And let's see, it works. Nice. So it's my great pleasure to welcome you all here at Svalbard, or on the island of Spitsbergen, like we Dutch people like to call it. My name is Gijs Breedveld, or for the non-Dutch speaking people, Gijs Breedveld. I'm head of the Department of Arctic Technology, and I'm also the research coordinator for UNIS. So it's my special pleasure to welcome the people living in Noordwijk, because that's of course a famous place for all from childhood onward. That's a place we would all like to visit. So on behalf of UNIS, it's very nice that all of you came here. And I don't know how many of you know UNIS, but I would like to give you a short introduction. Why are we here? That's the big question. So UNIS is the university center on Svalbard. And it's not a university, it's a company under the Ministry of Higher Education. So all we teach here is sort of accredited by the main universities on Svalbard, on the mainland, on the mainland. So there are 10 universities on the mainland. We have an agreement with 9 of them. So any course we plan or any student we host is sort of affiliated to one of the mainland universities. And that also is a basis for international collaboration, like the Marie Curie collaboration. So what is our mission here on Svalbard? That is actually to educate the Arctic experts of the future. That's the main mission. And that is a highly field-based and science-based education. That's the mainstays of our presence here. So we use the natural environment here around us as the laboratory. And I hope you will, during the coming days, have the opportunity to experience the outside and the outdoor laboratory, because that's where we work. So we live in our laboratory. And we are 70 permanent employees here. And what is important, I think, for you as well, I hope you get to learn more about it. We have a very strong logistics department. So we take our students out to remote places, both on land, on glaciers, in fjords, on everywhere. So we have the facilities to bring groups, researchers, students out there in a safe way and bring them safe back again. So I was myself last week for 4 days with my students in Svea, the old mining site where we investigated how is sort of the recovery coming after the mining site was closed. So I was a pleasure to read the conference, the topic of your conference. My own background is environmental engineering, and I saw that you can manage to monitor contaminants as well. So that's where I'm really interested in. So especially with these mining sites and how the runoff is from this remote site is very interesting. So just to show you our capability, we have about 700 to 800 students through the UNI system every year, and they are eager field workers. So I would advertise it here. If you need some field validation or calibration of your remote sensing data, include us in your proposal, include us in your ideas. We are happy to host any master and bachelor students or PhDs. So we really have this as an objective for UNIS. And I would just quote one of our green strategy, because you fit right in our green strategy for 2030. The objective 5 is that UNIS wants to be the international forefront in the operationalization of innovative observation technology field campaigns under Arctic conditions. And one of the action points is make use of Svalbard as a calibration validation site for satellite data. So you're right in. So I think it's a very well fitting that you're here, all here, and I hope you have a joyful time here. So thank you.
Thank you very much. The next speaker will be online, Yves from ESA. I will see if I can. Yes, over to you, Yves. muted, Louis.
I'm not muted now anymore. It's okay? Can you hear me?
Yes, we can.
Okay, let's try again. Can you see the slide now?
Yes, we can.
Okay, here we go. So I'm very happy to introduce this meeting, being the 20 years anniversary of SeaSAR, which we created a long time ago. You will see a bit based on historical work we did in SAR oceanography with colleagues in ESA, mainly from the ERS missions. Let's start by recalling the objective of this workshop. Why are we here? We are here to discuss for scientific exchange mainly, to assess the state of the art in the domain, and to look at synergy for coastal and marine application, to look at what we can do with these virtual laboratories, tools, digital platform. So what we want to, the final objective, of course, is to encourage close collaboration between all of you, but also to simulate the exploitation of the mission. We are talking about exploitation not only according to mission objective, but also beyond mission objective. We have the Earth Explorer in orbit and in preparation. We have the Copernicus Sentinel missions. I'll come back to that. And this is, of course, a unique opportunity to present some of the results we have achieved in the last years in SAR mission, application, and project. And also to formulate a number of recommendations. I think we need your recommendation for the future work, as simple as that. So we need to prepare from this meeting a roadmap for research and development activities that we could possibly fund with the ESA Earth Observation Program. It's called EO Science for Society. And this encompasses several domains: science, but not only, also application, downstream industry, everything related to digital innovation in the domain, and a new program element called Sentinel User Preparation. So this just keep this in mind during the week and make sure that with the several groups and splinters you will have during the week, you can prepare a number of recommendations for ESA, but not only for ESA, but also for the national programs and international collaboration. So going back to history, I didn't think I was going to show this slide, but it's really just telling that we started working in the domain in the 90s, and shortly after the launch of ERS-1 and ERS-2. We started to look also at the time from 1997 on calibration and validation of SAR product over the ocean. I think 1998, this is a publication which was organized by Yoni himself, if I recall correctly. We worked with people in the US on this wide swath SAR around the RADARSAT program and RADARSAT data in 2000. And then we had 20 years ago this coastal and marine application of SAR here in Svalbard, for which you have the publication here. And we have kept organizing regular meetings in the domain to keep the momentum. I just stopped here at 2013, but doesn't mean we have had no consultation in between. And just to say that with these 20 years of the ERS mission, it's also a milestone, an important milestone, because one of the fathers of the mission got the Nobel Prize in Physics, and it's really worth noting that this is a strong community with a strong scientific focus. So what we have done in between from 2013 to now is prepare a number of new missions. I was looking at this presentation of all ESA mission and trying to circle all the SAR mission we have. Of course, I mentioned already ERS-1, 2, and VSAT, Sentinel-1 A and B, Sentinel-1 C and D under the Copernicus program. But that's not all. We are also preparing for ROSE-L, Sentinel-1 Next Generation. And on the science front, we have also a number of extremely interesting scientific missions. The Biomass, which is a fully parametric SAR at P-band. The Harmony, I'll come back to it, which is the latest Explorer being selected. So we have been doing a lot of groundwork to give you missions to do to do your research and application development. So talking about Harmony, so this is the last Earth Explorer being selected by ESA, and it has really, it's comprised of 2 companion satellites flying in convoy with Sentinel-1D, and with a passive SAR and a multi-view thermal infrared instrument. So in part of the mission of, we have 2 phases in the mission, the so-called cross-track interferometric phase, which is mainly for land application, and the stereo phase, which is a phase which can contribute very interestingly to oceanographic application. I'm sure you will discuss this a bit in more detail during the week. Last but not least, this is also something we want really to promote and prepare for with this Sentinel user preparation element, which is a Copernicus Sentinel expansion and next generation. So here I'm fully happy because we have both a Sentinel-1 next generation, which is a fully polarimetric quad pole, and which allows, of course, a very interesting continuity and enhancement of the application we have done with Sentinel-1. And also a ROSE-L, which will be the first L-band SAR in Europe with quad pole capability, dual pole, and a number of interesting features we have been studying since decades, actually, with the ALOS mission from NASA in particular, or NASDA, sorry, NASDA and then JAXA. So that's really a good really basis for preparing the future, and we are looking forward to that. Now, if we go to a number of the success story we have had, there is this marine atmosphere extreme satellite data set production. Here we have been capable to generate with this activity an atlas of multi-source Earth observation over tropical cyclone, description of the swell field, global extreme wind intercalibrated between SCAT and radiometer, global merge multi-mission gridded wind data, high resolution vortex and wind structure from SAR imagery. So you see on the bottom left some image of Sentinel-1 over the cyclone, and on the right side a nice combination between SMAP and SAR for a typhoon. So just some illustration of capability. Here we see also on this example the value of international collaboration. So if you combine the capability of Sentinel-1, RadarSat-2, RCM, this is how you can track the longest ever tropical cyclone over a period of 2 months. So this is really a nice tool to improve the quality of cyclone and climate forecast. And this is really a topic we have been looking at. Actually, this activity was part of what we call the shock campaign, which is a campaign we had the idea to start after the launch of Sentinel-1 to look at how we can study a hurricane, generate data of a hurricane, and do science with it. It's called shock. So we can really do a lot with SAR. We can look at polar law. We can look at cyclone monitoring service, not only in the tropics, but also in the Mediterranean region. And this is an example of activity which was done under an open call on the left side. So open call means the as a community, you have the capability to submit to a proposal to ESA at any time for a new ID, and if selected, we will fund it for 1 year and a good budget. So other examples are the ARC Atlas, which is run by a NERSC, and I think you will hear about it during the week. We are able to characterize the Arctic amplification and its impact. You have on the bottom left the change in Arctic sea ice extent, and on the right you have some new features like ocean AD signature on SAR-derived sea ice drift, which is something very interesting, and you have the relevant publication. So let me continue on this other important project. We have organized a user consultation on the world ocean, which brought a lot of people at Esrin to look at what are the user requirements around this project. And we can develop really upper layer ocean circulation products from synergy between the different satellites. The SAR data are used, of course, to derive the current the Doppler, the famous Doppler anomaly, which was basically discovered by reprocessing some ERS wave data. I think Bertrand and his team can explain to you how he made the discovery. And of course, wave current interaction analysis when we can really combine altimetry data with Sentinel data. So an interesting topic. So to continue, we have a number of other new projects where we looked at the SAR wave, looking at next generation SAR product, including interferometric wide mode Sentinel-1 products. So we can look also at the synergy we can do by using in synergy optical altimeter and fully focused SAR altimeters. And I suppose this is a topic of discussion during the week. And a number of scientific research on the coastal wave, Arctic sea wave, and the assimilation of wave data into models. This is something actually we started a long time ago in 1996 with the preparation of the new cross-spectrum and VSAT. So I took this picture because I could not show Nazaré without a picture of real life of what's going on there with the people surfing the largest wave in the world. Now we have a number of tools we developed. So those tools are, they can be used for research, but they can use also for training next generation scientists. So the SIN tool is an example of that. I think you should all know it by now. It allows to enhance our understanding of the ocean science and the ocean circulation as well as a specific objective. We are using it during courses. So you will hear, I'm sure, during the week, maybe some of you have participated to this advanced training on the ship, on the tall ship. And this is some of the usage of the tool, including the deployment of buoys by the student during the January cruise. We are also looking at other things in terms of new processing methods. So on the top left, this is an interesting processing of what we call the microdoppler effects on a ship, which could be induced by a motion of antenna or just the engine running by itself. So, and we can use this to determine a number of properties of the target. At the bottom left, you see what is being done in terms of inverse SAR. It's a technology which is well known, but which is mature now. And on the top right, this is something interesting because it's the fusion of data from SAR, AIS, and this RF derived information from satellite using the capability we have with this company called Unseen Labs. So the combination of that is extremely powerful, and this is based on the Cosmos SkyMed high resolution data on the top right. So we are using AI as a tool. It's not new in the domain of oceanography. It's being used widely for a number of applications. And two examples here: the feature detection using radar imagery at the top, and some AI feature detection from optical imagery at the bottom. We are also looking at automated vessel detection. This is not a new topic per se. This was actually ship detection was the primary application of the ERS mission, but we are at a stage where we can really do SAR simulation and have an impression of the 3D reconstruction of a ship, and the corresponding application are the bottom left and center. The airplane is not really a SAR application, but this is also showing an additional capability. And some ship usage information, crude oil tankers at the bottom right. Last but not least, we are also working on new product, and the SAR video generated using this Spotlight extended dwell time with the steering of the satellite on the ISI mission is generating a new kind of product. So you can see in this SAR video a number of features over the ocean. You see, of course, the ship at the anchor moving. You could see this is really, it has a strong potential for new application, and the idea would be to have some data made available to the community for further exploitation. Another example, which is from this SAR video, is the you see an entry of a ship in a harbor, and you see, in fact, is a ship wake with time, and you see another one crossing. So it has a lot of new potential, still unexplored or untapped, as you used to say. So looking forward to future work on that. To do this future work, we have a number of instruments. Of course, we have the work we are doing through the Copernicus program and associated projects and services. I think some of you are in the room or are participating, and we can really use this knowledge to improve the service to the users and the exploitation of the data. We have also the ESA Earth Explorer program. So you see really the new capability we are preparing or exploring, and what we can do in terms of new science beyond the limit of what is being done today. We will continue, of course, to work with industrial partners, the research community, all stakeholders in the domain of marine and coastal application of SAR. And we will really look forward to future exploitation of the data in this program. So in terms of the instrument, we have the instrument is there. We have a program. Luckily, it's covering most of the elements we need to do the job, both the science, to deliver scientific excellence, the application, to pioneer new application, to look at the competitiveness of the downstream sector in the domain. We need that. All of this leveraging on latest digital innovation. We can also, we have, of course, the Sentinel user preparation. I mentioned it for preparing the upcoming Sentinel. And the notion of open call, you feel free to submit to ESA via the Futureo open call any topic in any of this domain that you see fit and that could make benefit from ESA funding. Just my last picture. This is years ago with Yoni and the Norwegian delegation, Per-Erik and Lisbeth, and we make sure that you continue to work in this domain and you have really a good meeting in Svalbard. I wish I could be with you, but I'm trusting my team and the young generation, and please continue the good job we have done in the last decades. Thank you.
Thank you very much, Hubli. You're sorely missed up here, but we'll try to keep the flag up nonetheless. So next one in line for the welcoming speakers, last but not least, is Johnny, and you're gonna tell us about how this whole thing works and how this whole thing came to be, right?
Thanks, Hero. Do you hear me well? Okay, so
you can just speak there also.
yeah, but I need to. Okay, so just to start by saying that it's a pleasure for me as well to welcome you all, and we are already 45 minutes late, so that's a good start. But we can't trust these airline companies these days anyway. So it means that we will gradually bite a little bit into the early part of the icebreaker in order to not lose the important time. So if I can have the slides, and where do I move them? Okay, like that.
Yeah, yeah.
Mm-hmm. Very good. So we are here, and just to recall a little bit the situation, we have plenty of you arriving into Longyearbyen from practically most part of the world, at least in the Northern Hemisphere, from Hawaii, China, Europe, US, Central, and so on. So it's a great pleasure to wish you all welcome. And in fact, thanks for coming. We also miss many. Many of those are online with us. So it's just you can just wave to them. You should have been here, guys, but okay. These kind of SeaSAR workshop, as Louis also mentioned, are fantastic opportunities to regularly meet and to discuss the latest findings and new innovative approaches dealing with research and application of synthetic aperture radar. Here we have opportunities also to see young career scientists starting to develop their career. And for instance, this young lad there, this is 20 years ago. Then he was young. He is no longer young, but at least compared to me, he's very young still. But he has had an excellent career as a SAR scientist. In fact, he is not just a SAR scientist. He's an excellent scientist in many ways. And it's also so that we can meet also older experts at these workshops. And the older experts are maybe this man, Werner Alpers. He is probably one person that if you go for his name, you will see him associated with practically everything you can imagine that deals with the use of synthetic aperture radar over the oceans. This is 20 years ago, and he is with us today as well. So it's a pleasure for me to have Werner here. He is turning 87 years old. So it means there's plenty of opportunities for us older guys as well in the coming years. And I've said that SeaSAR 2043, do not count on me to participate in the planning, but I shall be attending. So the issue is also that when we meet at these places, the SAR-based research that is at stake is possible to assess with good time. It's not the 10-minute presentation, rushing through 40 presentations. It is very much enough time for the presenters to go in details and for the audience to have a chance to hang on and in the end stimulate a very good discussion. So that's the key issue of these SeaSAR workshops. And hopefully the Space Agency listen to us and take into account some of our recommendations. I sincerely believe that they do so, but we need to be very precise and clever when we provide those recommendations. And I also believe that this is a format of a workshop in which we can also stimulate the next generation of researchers in SAR. And we need plenty of that next generation of researchers in SAR. So the series of SeaSAR family, I even noticed that I probably forgot the SeaSAR 2008 in there, but this is just a collection of some of them. So we started here in Spitsbergen in 2003. In fact, we did the first one in Johns Hopkins in 2000, in 99 or 2000. Then we came here in 2003, and we continued in Frascati in 2006, and crossed the Atlantic and went over to St. John's to do an ocean SAR there, led by the Canadians, also in 2006. Back to probably Frascati in 2008, I can't remember, and Frascati in 2010. Tromsø in 2012, Frascati again in 2018, and then COVID, and now back here in 2023. So this is an attempt to just project the plate of SAR, satellite SAR systems that we have. I'm afraid there could be some hiccups here that we are missing, but they should be more or less there. And we see this spread of SARs that goes all the way back to ERS in 1993, and Ben will probably immediately claim that where is SeaSat? SeaSat, in fact, was flying already in the late 70s and should have been on this one. But this indicates some kind of a significant continuity. And this continuity must be paid attention to, because it's through the continuity that we are able to really move forward with the research and application of SAR, as we will see and discuss in the coming days. The format of the workshop that you all have probably noted is that we are going to address the issues according to 8 themes. And each of the themes will have a plenary of 1 hour and 45 minutes, and it will have, I think, 6 or 8 hours of panel discussions tailored to that. The co-chairs will lead each of the plenaries, and they will also lead the panel discussion. They will also be the kind of initiators of the write-up of the white papers. So every theme shall have a white paper. And I believe and I hope that we can create a SeaSAR 23 proceeding, maybe similar to the one we did in 2004, but it doesn't have to be like this. But the point is that if we can make this in a printed version, we can do that. We have already debated this with ESA, and the agreement for that is in place. We can do that. It's a special treat that we are securing on this. And this is, in my opinion, where the reference document for the next generation of SAR experts shall sort of build on. We will discuss more during the week how we eventually will do this, what shape it shall take, and so on and so forth. So if you have strong ideas on this, you are welcome to sort of inform us about that in coffee breaks, at lunch, over a beer, or over dinner. But this SeaSAR proceeding will also have this recommendation, or the roadmap, so to speak, where we are going to highly emphasize where things has to go. And for ESA, as a space agency, they are going to refine their next strategy document in 2024. So there might be an opportunity here to invoke views to ESA as to how they should continue with their SAR development. And just one thing on that, we can't necessarily do much on Sentinel-1D or C, but Sentinel-1 next generation is where we can hit in. And dual polarization is something that we expect that the space agency are giving us. And that's one of the recommendations I would suspect. Then we also aim to do back-to-back papers that could be published in a special issue, review issue. That would benefit people who in the younger context are building up their career, and also with some of those that has passed the summit, we can also contribute to these papers. All in all, I think that this can be a collection of reference documents that sum up where we are today and project that into the next couple of decades. So the 8 themes are here, and you see the co-chairs, their names behind. The format in view of the presentations and the discussion now is not cut in stone like this, but ideally we have to have the understanding of the objectives. We want to understand the innovative new approaches and findings. We need to be very good in identifying the remaining knowledge gaps. And hopefully be able to outline how those gaps can be, in fact, filled, if not completely closed. And that will then connect into the outlook and recommendations. So you are all invited to be part of this. And I hope and I believe that this is going to be as an interesting workshop as the one we had in 2003. So before I close, I need to announce a few things for you that is also of importance. Coffee and tea we will have out in the big canteen area, and that will be set up in due time, I think around 16:50. We will have a welcome icebreaker here tonight in the same canteen area. where we can sit down, or we can mingle, we can walk around, and so on and so forth. So that's a good place to start the mingling. And there are two persons I want to acknowledge particularly for being very professional in the way all the pre-arrangement and organization for this whole SeaSAR workshop has come together. And that's Kat and Sabrina. So can you please stand up, both of you? Kat and Sabrina. Where are you, Kat? So you see, they are even so busy that they can't really follow everything inside here. So then with these words, I think it's time to start the first plenary. And that is the plenary on waves, wave retrievals. And what I want for every plenary, I need to have the co-chairs to be on the front row. And you see now the three guys there, Paco, Marcel, and Dr. Fab. They are there. And I think we have another one, Harald, should also come down here, because you are not supposed to hide away there, up there, Harald. And we do this for the other plenaries as well. And now I saw that Kat came into the room. So hi, Kat. Can you say hello to everyone?
And while we're introducing people, there are two people who haven't yet put their full effort into organizing this event, but they will. Anna and Petter are two helping hands, both master students here at UNIS. They are also people you should ask questions if you have them.
Okay, that's it for now. So we just continue with next on the first plenary.
Let's have a small break.
No.
Okay.
No break.
No. Slideshow. Beginning, and there you go.
Okay. We'll move the slides.
Okay. Hello, welcome. We are Marcel and Fab. I think I will start the presentation and Fab will keep me a bit in line. We have many co-authors that helped us to prepare this presentation. So I will not acknowledge them all, but because the list is very long. And we have also many slides, so let's get into it. So because we have a long presentation, I thought we fall with the door in the house and we just start with the main conclusions. And basically there are two main conclusions. We are now deriving spectra on a scene-by-scene basis, and we think that we should better exploit, let's say, the continuity of the wave field. So we can do that with models, statistical analysis, or with the firework technique of Fab. This should then enhance, let's say, our retrievals, and on top of that, we learn more about the imaging process. And eventually, what we will also see that neural network approaches are typically exploited for this. Then the second thing, and this comes basically from our studies with Harmony, is that we should not see wave spectra, wind, and Doppler as three different products. We should see them as a result from the same surface, and therefore they should be integrally retrieved or considered. So a little bit of an introduction. We have basically waves at the surface. They are basically the communication valve between the ocean and between the atmosphere. And for the climate perspective, what is very important are the fluxes, so heat exchanges, energy exchanges, momentum exchanges, and especially also gases. So that's why we are interested in these waves. And nowadays, we have many different instruments. So we always had already the synthetic aperture radars and the satellite LiDAR laser radar altimeters. Now we also have ISAT-2 flying, a LiDAR. We have CFOSAT, a spectrometer, and we have multispectral imagers. And this has fantastic capabilities, and they are we can use them in synergy to exploit all the data better. So a couple of them from the radar perspective are shown here. They have different incident angles, and that makes them also different, sensitive to different parts of the wave spectrum. And in that sense, they can help each other. So the Sentinel-6 is a nadir altimeter. You see that it mainly comes from specular scattering, and Sentinel-1 is mostly sensitive to resonant scattering. And all of them, they are sensitive to wave breaking. So a little bit about the imaging mechanisms. So we have the RAR imaging, and if not SAR is not applied, then we have only tilt hydrodynamic modulation of waves that are affecting, let's say, the backscatter locally. And then we also have range shifts, and normally they are not really considered in SAR, but we will see that if you get waves from an altimeter or a near-nadir instrument, then these range shifts become very important. From a SAR perspective, we have the famous velocity bunching, and this is a very strong effect, and typically in Sentinel-1, this is the dominant modulator. So in 1991, we had a big leap into retrievals because we could now map ocean wave spectra directly into a SAR spectrum and use that as a retrieval. However, this is very nonlinear, so it's not still not very trivial to do, and there are some limitations with this. But it basically comes down to a very long equation. And if you look at the second equation, you see all the parameters that are outside is basically a resolution loss. Then we have exponential terms inside. These are shifts in terms of Doppler shifts and range shifts. And then we have a term L, and this is basically the linear RAR transform. And they are connected to the wave spectrum S through the means of cross-correlation functions. We can add to this cross-correlation function another term, and this is what we call cross-spectral analysis. So we basically split the aperture, and then we have a little bit of time between two acquisitions, delta t. And then we have if you have a moving surface, we can exploit this to identify which direction the waves are moving. And on top of that, there is some other property, is that the speckle noise is gone if they are decorrelated. However, we cannot directly exploit these phases to get the dispersion because there are some processes involved, nonlinear RAR and SAR effects. And we can therefore not directly interpret this as a movement of the ocean. However, Harold Johnson has done some work, and with modeling, he can get quite close to what we expect to be the dispersion relation. But as you see, there are still some discrepancies between the blue dotted and solid lines and the red dotted and solid lines. So we are not there, but I think that Fred Nouget has an idea of how to close this gap. Then if you look at the lower wave numbers, the really long wave, then they come closer to this linear dispersion, and it does not really have to be considered directly.
Just to mention that this the previous one was using the wave mode, so where you create looks by splitting the Doppler spectrum, and This one is when you are using the TOPS mode and you are using the overlap between the different bursts. So there is no multi-looking involved. It's just looking at the overlap. And so in this case, first of all, the time separation is much larger than between two looks, like it's maybe 2 seconds, and the look direction is the same. And so in this case, we see that the TOPS mode phase is quite well following the dispersion relation in the overlap area.
But be aware that the range wave number is not exactly the same. So it's really the longer waves that follow the dispersion. Okay, then there are a couple of parameters that we get from the core spectra, and one of them is the Imax. And it's Imax that is basically the integral in the range direction between 20 and 15 meter wavelengths. And as you can see in the picture on left, right, that it has a nice wind direction sensitivity. So we did this over a depression, and then you can really see that that we can get the direction to the first order of the wind. So in the SAR wave project, this is further exploited, and what you can see is that in the VH polarization, we have something that is very insensitive to the incident angle, and on top of that, we have a very strong connection with the wind speed. And typically what we expect to use this for is to get the direction of the longer waves and not really the local waves. So we consider different scales in that sense. Then we have another parameter that we can estimate. This is the cutoff, and the cutoff is a proxy for the velocity variance and the decorrelation. And this is typically exploited to get, for example, this wave orbital velocity here in the bottom, and to constrain also the wave age of our wind wave system. This should be then together with the NSES, which is a proxy for the wind speed itself. And typically, this is used in the first step of the Sentinel-1 spectral inversion algorithm, where we remove the nonlinear part or the wind wave part of the spectrum. Then, just to show you that this not always goes right, so in the top we have cutoff estimation over very limited roughness. So sometimes this goes completely wrong and we're completely off. So the blue and the red lines, they indicate the model and the actual estimated cutoff. If waves are propagating in a certain direction, for example, in the along track direction that's in the middle, then it can also go wrong because it leaves in the autocorrelation function some kind of modulation. And when waves are propagating in a cross-track direction, it can also go wrong because it's either too wide or too small, depending a little bit on the wavelength and the strength of the signal. A possible mitigation is to use the second derivative of the first legs of this autocorrelation function, which Fab will show you later. Then there is another parameter which is not actively used at the moment, but still calculated in the Sentinel-1 product. And this is the spectral width. And the spectral width is a proxy for the NRCS. And I believe that this comes from its relation to the velocity variance. And this can be used, for example, for calibration. And I think it's a little bit more a stable parameter to estimate. So it can also be used to infer actually the velocity variance instead of using the cutoff, which is sensitive to the longer waves. Then I will give the floor to Fab, who gives you something about the retrieval algorithms.
Thank you, Marcel. So yeah, just to let you know, you can interrupt us at any time if you have any question or you want to have some precision or what we are saying, because we had to compile a lot of slide information in a few slides, so sometimes it's quite dense. So for the retrieval algorithm, so originally there has been the closed form approach, which is to try to invert the forward SAR transform. And so there have been two main approaches: the so-called iterative Max Planck, which is basically starting from a first guess and start to iterate the forward transform until it converges to to what you expect, and then have been the self two-step approach, which doesn't rely on any a priori, but just use the cross spectra, and is actually running a quasi-linear inversion after removal of a non-linear part that is taken from a lookup table, and the lookup table is derived from the forward transform. And so that are the two approaches that have been two traditional approaches that have been proposed so far. We will see that lately there are many attempts to use a neural network to perform this, but they are not yet to the estimation of the 2D wave spectra. So there have been some assessment, some investigation of the quasi-linear inversion using buoy data in many areas where we have actually a measurement from a very nice buoy measurement device, and then we have the SeaSAR image where we have an atmospheric front, and so the wind is very different from one side and the next, and so that are typical cases that are interesting to question the inversion. And in this case, we see that on the left is the inversion, and on the right is the actual observation from the buoy, and they are quite different. And also, we must say that when the wind sea is starting to build up, like on the upper right part, and if it's closer to the azimuth, it will not be seen by the SAR. So this is one of the limitations of the azimuth cutoff. Okay, and so in fact, when we have a typical azimuth cutoff of 100 to 200 meters, we see that if we start from an actual wave spectra, which is here the prior, we see that the actual SAR transform is really cutting a lot of information in the azimuth direction, and so it's kind of difficult to get back this information at the right place after it has been so much distorted. So in fact, there are inherent limitations in the SAR wave imaging that makes it not really possible to retrieve very short wavelengths in the azimuth direction. But this is well known. But for the swell, it's a really very excellent instrument. So to sum up the known issues of the closed form that we use today, so for sure there is a limited spectral coverage, especially in the azimuth direction. We know that the time varying geometry within the observation dwell time is also is not well properly taken into account in the closed form. So we have people that have already found some way to modify it, but it will be presented in a breakup session. So the cutoff is also affected by different other parameters, and it has estimation issues, as Marcel was showing. And so you have also the so-called supercritical wave velocities, that the velocity bunching mechanism imaging mechanism is somehow providing some modulation on the SAR image, but when the waves amplitude is so large, this can be supercritical and destroy completely the modulation. So, and this is a known issue also. And also the RAR response is somehow poorly understood, because we are still making some assumptions that are not always. So I think I will show you on this one. One of the issues on the RAR modulation is when you have a wind following the swell, and then you have the modulation. The RAR modulation is actually much reduced compared to when the wind is not following the waves, and this is clear from this SAR image, where it's a swell system that comes from very far away, and when it crosses an atmospheric front, we see that the amplitude modulation gets much higher. So we have also some estimation of the wave modulation by the diameter of the small dots, and we see that the swell, when it propagates out of the storm, it's not going to gain and it's not going to gain any intensity when it passes the atmospheric front with the wind facing, which is just the actual RAR modulation that is changing fast in this case. So the supercritical velocity and slopes is just here an example that was taken from SAR wave imaging in sea ice, because actually in sea ice the imaging mechanism is much easier than in open ocean, because there are some, for example, the cutoff is almost negligible, because there are very few short waves propagating in the sea ice that are disturbing the signal, and so we see clearly that the velocity bunching is increasing the modulation up to a certain point, where you start to have some double peak, and then it will start to reduce the amplitude modulation when the amplitude is going over this supercritical slope. So the time varying geometry, it's something we discovered by looking at the imaginary part of the cross spectra, and we see that in some cases we have an inversion of the sign of the cross spectra imaginary part is used to estimate the wave propagation direction. And so when we have swell coming from very far away, we basically know that the direction will not change 180 degrees suddenly. So then we wonder why there was this inversion of the sign. And in fact, Fred come up with this picture where we have even if the SAR aperture is quite small, it's of the order is less than 1 degree, but still within this small angle, you have a small variation of the cross section along with time, and this modification is actually creating an artificial phase that in fact can be interpreted as a propagation phase, but in fact it should be corrected for before you estimate the propagation direction, because these are especially for the long swell, the phase is very small, because the time difference between the two looks are of the order of 0.1 or 2 seconds, and so the long swell that have a 500 meter wavelength, they will not move much in this small time. So we also so this is basically the same effect but in average. So we could see that there is in average a phase plane in the cross spectra. So and this is also this is explained by what I was showing before. So in fact, we have to be careful when we use the cross spectral phase. There is something that is due to the varying geometry. It's not only the geophysical velocities that we observe. So this is just to keep in mind. So next, I will talk about the new approaches to estimate wave parameter from SAR. So which is clearly the neural network and the machine learning approaches. So there have been many attempts, at least 4 of them I will present from 4 different groups. And so the first one here is from Stopa and Mush, and then have been further developed by Quash. And it's basically taking the SAR image plus the cross spectra plus a few parameters that are the convolution of the spectra with the different filters, and that's the parameters you're in the sea wave approach. And then from that, you start to estimate. You want to estimate here the significant wave height. So this has been quite successful. This has been further developed by other people in a different group, but still having some quite good result on estimation of the HS WinC. So the first one was the total significant wave height. This study is for the WinC significant wave height, where they had quite good also result, and by adding some few more parameters, like the Imax, which is the imaginary part in the cross spectra. So there have been also some attempts to derive the actual 1D wave spectra. So we are not yet to the 2D wave spectra, but this one is an attempt to retrieve the 1D spectra from image spectra, and this has been using a LSTM type of neural network, and with some quite promising results. So this is also something that we hope will at some point be transferred to the 2D spectra. And we had also a group at DLR that developed a methodology for retrieval of significant wave height, and now some other integrated parameters, like the mean period, the WinC period, but not yet the 2D wave spectra, but running something quite, I would say, operationally this time. So this is something that is really developing, and is start to being used quite regularly. So this part of the state retrieval using neural network and machine learning. Here it's not a neural network, but it's a support vector machine. But this is using the statistical properties of a big data set to estimate after an estimation for a given snapshot. And so this is one of the results from this last algorithm that is part of the SAR wave study. So they have been comparing with buoys and models their significant wave height estimation, and we see that we don't get too much of a underestimation at high significant wave height. So that means that this technique are really starting to be quite useful, at least for significant wave height estimation in extreme condition. So the main limitation of this new neural network approach, so it's for now it's only retrieve the integral parameters, not the full 2D spectrum. So there are also filters applied to capture various scales that are not causal, so it's something to be considered. Not all the parameters are fully used for now, and there are some input parameters to the method that are still suffering estimation issues, so that will impair the results. And the neural network are still suffering from the single line of sight of Sentinel-1, meaning that this azimuth cutoff limitation makes the neural network not able to retrieve what has been completely lost. And this, if you will gain from having different line of sight in the future. And so, of course, if available, multi-sensor constraint can help to the training of this neural network, and also the exploitation of improved ocean wave model will help, because most of the training data set for this neural network are still using models, where because the in situ data set is still not big enough to train this network, but it will come also in the near future with the network of wave drifters. So then we had the swell tracking from synthetic aperture radar, which has been developed to actually making use of the consistency between the different observations that are actually looking at a swell system, the same swell system that was actually generated by a distant storm, but that has been seen at different angles from the storm and at a different time of propagation. So in fact, this technique has been applied first with the wave mode of Sentinel-1, but we see that there is not so many wave mode data in the North Atlantic. This is because the acquisition mode in North Atlantic is not the wave mode. by default. So in the Pacific Ocean, it works really well, but not in the North Atlantic. And then we can, when we add data from the SWIM, which is a wave scatterometer, which is a rotating wave scatterometer that just measure the 1D spectra in each azimuth. So there is it's very complementary to Sentinel-1, and the data are also now available in real time. But still, when we add the Sentinel-1 IW mode, which is a very wide coverage on the Northeast Atlantic, we had a lot more observation to the swell tracking system, and we can really have a good monitoring of the swell arriving on the European coast. And so this is making use of the new cross spectra estimated from the TOPS mode of Sentinel-1. This is part of this new SAR wave project, and where we see that the TOPS mode is composed of several bursts in azimuth, and if you look at the overlap between the bursts, which is called interburst, we see that the imaginary part is quite it's not too noisy. Whereas if you look at the intraburst, which is the usual method we use for the wave mode, the imaginary part can be much more noisier because the time separation between the looks is an order of magnitude smaller. So that's quite promising in terms of swell tracking to use the TOPS mode now. So it's just a demonstration. It's not used operationally now, but it's under development. So the swell tracking has also been used to look at tropical cyclone generated waves. So also combining satellite observation from Sentinel-1 wave mode with the SWIM wave scatterometer, but also now we have a large network of drifting buoys, the wave drifters, which significantly increase the number of observations in the open ocean compared to the Copernicus in situ observation, which are mostly coastal and are very scarce. But overall, when you combine all these measurements, you can have a pretty good description of the wave generated by a tropical cyclone. So here again, you see that the Sentinel-1 has very little observation because it's the North Atlantic. If you would add the TOPS mode, it would be probably much larger number of data like the other satellites. So this wave spectra from Sentinel-1 are assimilated into a sea-state model. So this is just an example of assimilation of test with and without assimilation for wave radiating out of a tropical cyclone Freddy. And so we see that without assimilation, the waves are underestimated, basically, because most likely in the wave model, the wind forcing is too low for the high winds, and therefore the waves doesn't have the right intensity where the observation can see it nicely. So there have been also some experiment of assimilation in the icy waters around Antarctic, and we see that the model is overestimating the significant wave height, and we can think of also that that's partly due to the ice and the icebergs that are attenuating some wave energy. And if you assimilate the observation, you have the actual field. And when you compare to altimeter significant wave height, you have a much better, smaller scatter index, especially around Antarctica, where you expect icebergs than with the wave model. So this is another assimilation experiment of it's a compared assimilation experiments. So it's an assimilation using SWIM compared to assimilation using SAR. And that's the difference. between the significant wave height in these two assimilation experiments. So basically, what you should see here is that when you are in a red or orange color, that means the SAR is bringing something to the assimilation, and in blue is mostly the SWIM scatterometer. That so in fact these two are quite complementary. The SWIM scatterometer is better able to estimate the wave spectra in the Southern Ocean when it's very high winds, and it's very nonlinear for the SAR imaging mechanism. And at the contrary, in the tropical area, the SAR is able to track very well the long swells, and it's bringing something in the assimilation that the SWIM cannot see. Okay. Oh no, okay. So finally, since we are in Svalbard, we wanted to show some wave observation in sea ice. So this is on an island on the southeast of Svalbard. And so you have a swell coming from the southwest, the lower left of the image, and it's turning around this island so it appears from the south, from the east of the island, and from the west on the northern pine of the island, and then it's crossing again. And we see that the actual azimuth cutoff is very low, so there is no azimuth blurring in this image of wave in the sea ice. And you see that this wingling pattern, where you have the velocity bunching of the swell coming from the south, it is modulated by the velocities of the swell coming from the west, and that are creating this sinusoidal wingling patterns. And so this is something that we have analyzed and published in 2015 and 17. And so from this pattern, you can actually estimate the orbital velocity of waves and come back to the wave spectrum. So if you read the paper, Arduin et al. In 2015. And what is striking also that I was saying is that when you have open ocean, immediately you see that the azimuth cutoff is quite huge, and it appears like a little blurring in this imagette. But we see that when we have ice cover, the azimuth cutoff virtually is much reduced, and so the imaging mechanism is easier, and also the retrieval is expected to be more accurate. And so I wanted also to show you some observation of iceberg reflection. So I don't know if we don't see clearly because it's too small. We should have zoomed it more, but in fact, around these icebergs that you see in bright, in fact, you have radiating waves, circular radiating waves, which wavelength that is much smaller than the incoming swell that you see here. And so that's why at this resolution, and unfortunately, I'm not sure that you see it, but yeah, okay. But actually, around these icebergs, there are circular wave pattern at very short scale. But here it's quite difficult to see on this plot. But I will be able to show you later on if you're interested. And so the synergy of observation of wave and sea ice is something that is really important because we have a lot of possibility for wave observation in sea ice. So of course the SAR is one of them, but we have also the interferometric SAR, like here it's a tandemix across-track interferometry, where you have the actual estimation of the elevation. So you can measure the field elevation directly. And we have the ISAT2 laser altimeter that can be very useful in cloud-free condition to estimate the wave properties. This has been shown to be quite successful, and also in cloud-free condition, we have the Sentinel-2 that has a nice signature of the swell in the sea ice, and also the newly developed fully focused SAR altimetry that actually provide an imaging capability from altimeters such as Sentinel-3 and Sentinel-6. And so there are still some work ongoing to disentangle the signal from the left and right part of the nadir. But since the wave properties are quite well known, there are ways to using the cross spectral technique to separate between the left and right part of the source. But Marcel will talk about it after. And so last thing I wanted to say on the wave measurement in sea ice, we can also estimate the amplitude attenuation of wave in sea ice. And so we use simple technique of demodulation and estimation of the envelope amplitude variation with distance. Okay, so this, in fact, from that we can have an estimation of how far the waves are attenuated, how strongly the waves are attenuated in the sea ice, and hopefully this provide information on the sea ice itself. So there have also been some analysis of the polarimetric and multi-frequency observations. So here is from several instruments, like maybe hopefully Sentinel-1 next generation. We have full pole capabilities, and we can benefit from this, the difference in all these polarimetric images to retrieve information on the wave. So we know that, for example, the wave breaking, they have a signature very similar in VV and HH polarization, whereas the Bragg wave, they are quite different. So we can learn a lot from this polarimetric diversity about wave observation. So wave field continuity, this is something that also was developed when we are using a large image that we subdivide in small sub-image, and we estimate wave spectra on each of them. Then we use continuity to invert them into a consistent swell field, because sometimes the propagation direction ambiguity has some hiccups, and you can have a reverted waves. But if you use continuity, you can from any SAR image in WISE-FOSS, you can estimate a quite consistent swell field. So this So finally, I also want to talk about some work that has been done in demodulation of the wave amplitude. So we know that when the waves are propagating, they are propagating as wave packets, the so-called group. And so from the SAR image, we are able to first we try to isolate the different swell components or wave components in the image. So we do some partitioning, and then we obtain only one component of the swell field, and then from demodulation technique, we can estimate the group properties. So the length, the width, and the direction, and compare this direction with the actual direction of the wave spectral peak. And so if we have very little nonlinear distortion, usually the direction is, as we see, the red and the blue direction really align well together. But then when we start to have more and more nonlinearities for the wave system that have a smaller wavelengths, we start to see discrepancies between the group direction and the peak direction. And when you are strongly affected by the cutoff, that's where you have the maximum difference between the group direction, the estimated group direction, and the peak direction. So that's also one of the techniques that could be used to assess how badly your retrieval is affected by the cutoff. So then I will let the floor to Marcel.
Thanks, Fab. Okay, we are still missing a couple of sensors because up to now we have only been talking about SeaSAR system and CFOSAT. So actually what some people believe is that Sentinel-2 is the best way to retrieve wave spectra. And I will show you in a moment why this is the case. It's really fantastic what you can do with this instrument. On top of that, we have a couple of radar systems. And as you can see here in the, let's say, in the colored parts, they are sensitive to different parts of the wave spectrum. And because they are sensitive to different parts, they can help each other to constrain, let's say, what is actually going on the surface. So if they are used in synergy, you really get a grasp of what is going on, and you can learn from each other and calibrate, let's say, the retrieval models on each other. Okay, first I will go to the Sentinel-2. So this uses basically sun glitter. It's sensitive to the directional roughness, but also sensitive, the modulations are sensitive to the direction of the waves. And you can see in the right bottom plot that except for one particular line, we can basically retrieve the whole wave spectrum. And we are not sensitive to any cutoff anymore. So that makes it, in that sense, a better instrument than SeaSAR for this. But of course, it doesn't have all weather capability, and the sun has to be in the right location with respect to the surface and the satellite. Then here is another example, and let's focus a bit on the right side. If you see the two right figures, we can really retrieve the one-dimensional spectral energy very well, and also up to very short wavelengths. And on top of that, we can get the phase velocity by using two channels of the system. And these two channels, they are recorded with a slight time difference between it. So we actually get the dispersion. So then another instrument that we didn't address yet is the SeaSAR altimeter. So since short we can process fully focused, and we can get very high resolution over the ocean. And then if you look in the waveform tail, so that is panel A, you see all kinds of signatures that are coming from waves. If we try to normalize this, so that we do in panel B, and then we crop some part of the waveform tail in C, then we can actually get a spectrum that is similar to the spectrum that we have for the SeaSAR systems. So this is an example. So we have Rania, who was one of the authors on the paper, and she went to CLS, and they have been working together since then. And what you can see very nicely in A and C is that you have some crossing patterns because you are sensitive to two sides of the altimeter. So basically the left side is flipped and mapped onto the right side. So that's why you do not see a single system, but you always see two systems, which is actually one. But if you then pass by an island, so that is in case of B, then you only see one side, and then you indeed see only one set of lines instead of these crossing patterns. And in the bottom, you can see that for a very long swell, you can actually get quite well the wavelength or the period and the direction. So we have been developing this a little bit further in the SeaSAR wave project. And actually, an overpass of an altimeter has 2 seconds of dwell time. So you can compute many, many cross spectra. And in fact, you can compute a cross spectral stack. So that's what is done here in the right side. So we created, in this case, 5 SeaSAR spectra. And because you are sensitive from you're looking from different directions to the surface, you're sensitive to different parts of the wave spectrum, directionally speaking, and then you're able to retrieve more information about the system and have better constraints. And if you look at the bottom, that are the imaginary parts. So you can also see that we see an effect of which is basically the dispersion. And on top of that, we have a little bit of an effect of a changing phase due to a different geometry from left to right. So then the final part, I want to talk a little bit about the future. And this is developed a bit in the context of Harmony. We are busy with multi-scale integrated retrievals. So as you know, all these waves in the wave spectrum, they have different wavelengths, but also different relaxation scales. So you should never consider, let's say, a wave as a point measurement, but it's part of a whole. And in this particular example here on the right, I show that basically the backscatter, the Doppler, and the intensity spectra, they are providing information to all 3 level 2 parameters. And if you then insert a wave model into this, but it could also be a statistical model or a neural network, whatever, then you can iteratively improve, let's say, the actual wave system and get, let's say, an integrated retrieval for the whole field in the same time. So there is another attempt in this. This is from Ifremer, where they basically use more parameters that have been used before. So we put max in the C-wave parameters, the Doppler, into a neural network, and then we try to retrieve integratedly all kinds of parameters. So in this case, they primarily focus on significant wave height, I think, but this can be extended, as we already saw from Andrij's slide. Then finally, we have a couple of approved and proposed missions. I will not pass by all of them, but we have been working a bit on Harmony and SeaSAR and Sentinel-3 next generation. So I will address them. And on top of that, there is an exciting concept, SwarmSAR, which is in the early stages of development. So basically what you see here on the right is that I modeled here a tropical cyclone, and then I computed basically the closed form spectra in different parts of the cyclone. And in some cases, you can see that you barely have any information. You only get the wind system and not the swell system, or you get nothing at all. And you can also see that the cutoff, depending on where you are in the tropical cyclone, is varying. So if you have multiple lines of sight, you have a better constraint because you actually cover a bigger part of the SAR spectrum, and that's what we show here in the bottom. So we go basically from the left, Sentinel-1 spectral coverage is only about 10 to 20% in these very high energy systems. But with Harmony, we go up to 40, 50%. So that's an improvement of about 2 to 2.5. On top of that, we have also polarimetry, which can help us to constrain things like wave breaking and the RAR in these kind of systems. Then we have SeaSAR. It actually has a better line of sight diversity than Harmony. And it's a bit a question on what kind of resolution we can achieve. But in principle, this would also be a wonderful instrument to get wave spectra. And on top of that, we have better constraints because we have 3 lines of sight. We have a better constraint on the wind-sea system. And we expect to, if it gets launched, we expect to see a very nice result from this mission. Finally, we have the Sentinel-3 next generation topography. This is a SWAT altimeter. And this is maybe interesting. I just wanted to show you something because we have been talking about the cutoff. So that's the equation on the top right, which depends on the velocity variance. But in the case of an altimeter, you also have a cutoff in a cross-track direction, which depends on the significant wave height. And as you can see, if you have a nadir altimeter, the cutoff is very narrow. So you immediately go up to a cutoff of 200-300 meters. But in the case of the SWAT altimeter, you have very strong range bunching, but you do not really feel the cutoff yet. So typically, as a little bit of a ballpark number, you get to, for an nadir altimeter, it's 90 times the significant wave height. And for the cross-track altimeter, it's something like 12 times the significant wave height. Then the last one is SwarmSAR. So this is a concept mission. It's a MIMO system. And actually what we try to achieve here is that we use multiple satellites and then we can overcome this problem of decorrelation. So if you have multiple satellites along track and you process the signals coherently, once you get the timing right, then you're actually you would actually be able to see the waves and also the wind waves. And in this particular situation, you can see here in the bottom that the azimuth resolution goes from something like 300 meters down to about 10 to 20 meters. So we have the summary and conclusions. I already mentioned a couple of them. In the last years, let's say since the first Svalbard SeaSAR, we have limited improvements in the closed form retrievals and the emergence of neural network approaches. Current work shows that we are still improving into the closed form, can have improvements in the closed form. But I believe, and I think FAB also believes, that the future is a bit the neural network integrated approaches. And we should also consider multiple sensors to constrain, let's say, everything that we have at the moment. Because our models are far from perfect. And there is a lot of data and parameters that we can still exploit. As part of this current work is also the SARWave project, already mentioned a few times, and there is a website for this, so you can go there and see what we are actually doing. Then a few recommendations. So we recommend that we use multiple polarizations, so for example from radar set, to constrain better the RAR and to also constrain better the, let's say, the fraction of wave breaking. We can use the wave drifter network that is still growing, especially for sea ice, learning and validation. It's very important. The use of the wave retrievals, which is done up to a very limited extent in sea ice, is very important for the miss monitoring. At the moment, we are actually busy with level 1, basically we go back to level 0 before the SAR processing, and we take into account, let's say, the behavior of the ocean into the SAR focusing, which could be exploited. On top of that, we have RAR information that we are not exploiting at the moment. And then eventually we want to have open source software so that everybody can learn from this knowledge that is being generated. Then a few more recommendations. So like I already mentioned, we want to have multi-sensor synergies. Then the multi-scale integrated retrieval approaches, the MIRO algorithms. And then eventually we have to focus on retrieval algorithms for future missions. Because if you really want to go to high resolutions, we are still quite far away from getting what we want. Yeah.
So is that it?
Yeah, I think so.
Okay, so that's the end of this integrated presentation. So now we are, if you have a question or a remark or a recommendation about what we have said, you can start to discuss that, and then we'll continue in the breakup session, and eventually we'll wrap up that in the plenary session on the last day. So, do you have any question or remark on what have been presented?
I think Andra wants to explain a bit more the methods.
Yes.
Ekaterina Kim from Norwegian University of Science and Technology. Thank you very much for this overreaching presentation. Just looking at so many recommendations you mentioned, if I have to like little bit challenge you, if I give you like three, if you have to prioritize three, could you prioritize three out of what you have been talking today?
Yeah, but I don't want to be too much biased. But no, I think that the multi-scale integrated retrieval, it's something that will benefit from all the retrieval of the individual parameters. So this is a must do. And as I was saying, using the wave retrieval in the CIs, we learn a lot on the SAR imaging because it's actually a simpler mechanism than OpenOcean, and it can really provide some interesting methods. So of course, there will be always the need to improve the retrieval and to start from the level 0, use the swirling transform. And there are many things that we want to do, but in terms of priority, that's what I think.
What I believe is that without the integrated retrieval, you will not get to high resolution. So if you want to get there, then do this. That is the thing.
The Fab is, I think it's really the waves in CIs is really mature. So I think we can go forward and provide something to solve many issues in, for example, in operational wave models related on what you show. For example, we have a very big uncertainties in sea ice fraction and also the fetch conditions of generating the wind wave in the marginal ice zone. And really using the wave retrieval in sea ice can improve such fetch conditions and also improve the wave ice interaction terms in the wave models. We are missing
sound.
Yeah. We are missing battery. We are missing the wave input in the ocean mixed layer under the sea ice in the marginal ice zone, and we know that waves are still propagating under the sea ice, and this mixing is important in terms of ocean circulation, salinity, temperature, and all these ocean key parameters.
Just to mention that, in fact, for wave propagating in sea ice retrieval, we were still lacking of in situ measurement of wave in sea ice to validate the retrieval, but now with the drifting buoys, we start to get a lot more, and so we'll be able to validate the retrieval now with this drifting wave buoys that are being developed by people like Eunice.
Yeah, just a very quick comment for the wave penetration in the marginal ice zone. So the altimetry people that try to measure the thickness of sea ice through the traditional freeboard processing, these waves are a pain. They are a massive source of uncertainty. Just saying.
Thank you.
One other question back on to the fireworks. And this fireworks we've seen since Anvisat, and it's done.
There's a 30-second limit.
Yeah.
Yeah, it's a 30-second limit, and then you got your time. So next question by Bjorn.
I can come over to you. I can use this? No.
I'll take this one.
Okay, so no, it's the fireworks and this issue about swell tracking that that you say you have control over now, and you could even extend it also with a combo of the different wave mode and wide swath and also the swim. So what does it take now to basically turn this into potentially a product that we could see transformed or transferred to Siemens? It must be a highly important quantity. And I also question Lutfi. It is in CMAPs.
Yeah, in fact, the swell tracking is already a CMAPs product, and Romain is well here at CLS to say that because he's responsible of this product. But it's not yet taken into account yet the TOPS mode from Sentinel-1. So in the North Atlantic, it's lacking a lot of data. Yeah.
So what's the how much we have to pay?
Gilles, do you want to answer this question? No, but it's something. It's a prototype that we have now that we have developed in the SAR Wave project that was kicked off a few months ago, and so this will be a clear outcome of this project to then transition it to the Siemens product.
Yeah. Okay, regarding the operationalization of this product, then we are taking a stepped approach. So first we will include the cross spectra for the TOPS mode, and this should be available in the first quarter of next year. And then after that, profiting also from the outputs of SAR Wave, we go full to the swell inversion, and this is maybe in the next couple of years. But that's the roadmap.
We have a couple of questions online.
Yeah, so we'll take a couple of questions online.
Christine,
what is the status or prospect of SwarmSAR?
Aris.
Yes, so can you tell us what is the status or prospects of SwarmSAR?
Okay, yeah. Yeah, I think I was first. Sorry.
Yes, specific question.
Okay.
Okay, so for SwarmSAR, basically for the waves, when the SAR system flies over a specific scene, the scene always changes and it adds the decorrelation. And because of the decorrelation, it limits the aperture time. And because of the limited aperture, it's difficult to get a high resolution image. So basically, when using multiple satellites, you stitch the aperture together if you get the timing right. So you can generate a very high resolution image. So it's in the early stages. So this is basically a concept. So we are still working on this concept, basically.
So, okay, thank you. So the status is that it's still in a concept level. Yeah. Okay.
This is also one of my hobbies, the SwarmSAR. So this is a study we did. We got some funding we got some Dutch funding to look into it, and we did some preliminary studies and dimensioning and whatever. And we have some follow-up funding. So we're doing something that we are going to be doing some technology development in the coming years on the SwarmSAR concept as a whole, but not really on the ocean applications. So if you really want SwarmSAR for the oceans, then somebody should put some money. And then we will gladly look into it. But it would work well, right? It's like a good combination. But status is looking good, waiting for money. Maybe. Then you need a PI, not me.
Andre will explain a little bit more Andre, we put for you the slide up because I think this is a bit the way to go. You already managed to get multiple parameters out of these neural networks, and maybe you can address this particular neural network a bit better.
Hello?
Yeah, we can hear you.
Me? Okay. So, what is exactly the question?
No,
Can
you
repeat the question, please?
You wanted to explain this particular retrieval method of yours a little bit better, because you are the one that. Okay, go ahead.
Yeah, okay, shortly, yeah. What is important in our algorithm first? It is combination of linear approach with machine learning. It means you have two solutions. First, linear solution. It is a fast solution. You need not no. It is you can use it as a first guess for your machine learning, but you can have a both. It's a very nice combination because machine learning need more capacity and time. And this, and first, second, this algorithm, in comparison with algorithm presented before the slide, can make not one parameter but 8 parameters. Not only significant wave height, but also the periods, swell, dominant, secondary periods of wind, sea, and you see, 8 parameters. And also, it is important, we can process, it's not only for one image jet, then completely fields. You see example. So we can process it in raster, in the fields, completely fields, and one field by processing by example 3 kilometer raster, you have 5,000 value per one image, and you can process it in our algorithm can process it in during 1 minute. So now, and most important, our algorithm completely is not is independent from cutoff. No, cutoff influence our results maybe 1%, not more. No, without long discussion, cutoff is make no sense in to use our algorithm. You can use it or not. Now, because we use 5 different kinds of SAR features. It's not only the statistics of an RCS, but it also gray level coherence matrices, the combination of pixels. We have also wind, we have also the sea wave parameters, and also the parameters of the FFT spectra for different wavelength domains. So this algorithm is very stable and can process fastly an image. And it is not only algorithm, but it's also software implemented for different satellites. We made it for now 8 different, 5 different satellites now in modes. It's working in near real-time mode. It means in 10 minutes after acquisition, you have completely processed fields sent to users. No? And accuracy, for example, wave mode is about 2 centimeters better than accuracy for algorithms presented before using neuronal network. So accuracy at the moment is directly dependent on the resolution of the pixel in the image. You can see in the last line now it is accuracy for different satellite and modes. You see 25 centimeter accuracy. It is for Sentinel wave mode. Now about 40 centimeters for EVA. And also it is implemented in the near real-time service. You can see in the workflow a daily processing for sea state in the North Sea and the Baltic Sea. And now, if you show a next slide, please. So now we process it and completely. It is practically completely archived 2020 for Sentinel EV. This about validated with a model. We validated only to a 60 degree in the north to avoid ice coverage. It is about 8 million collocations. Now you see Hermessier, and it's about 26,000 collocations with all possible buoys from different systems. So it is, we made this now, and now also the same function is made for an over mode for Sentinel and for Terrasa X. Also, we use this to reprocess the completely Sentinel wave mode archive with about 15 million values. So it already, but it's not a possibility to show this all here. Yeah, it was shortly.
Okay.
Thank you.
Just to give a little bit of perspective, an altimeter measures significant wave height with an accuracy from 20 to 30 centimeters. So you're actually already approaching the altimeter.
Yeah, the difference is we have fields, not in the point. We can show completely structure in the fields. So on accuracy, I'm sorry, I don't believe, because we know now you have a ground truth uncertainty 25 centimeters. If you compare with the buoy with the models, I made it cross comparisons, different models, different buoy systems. You have 25 ground noise in your data. Of course, if you compare altimeter with some radar instrument, you can get better accuracy. So not accuracy, but RMSE. And in comparison to
I really suggest that that the altimeter be used also to validate this algorithm, because then it's a direct measurement. It's not going through a model or.
I'm sorry, I made a PDF function for the altimeter for Sentinel and other results, and altimeter has more problem with sea state between 0 and 1.5 meter.
We know that.
Yeah, we know for short.
My algorithm doesn't have. I have no possibility. Okay, to show here PDF comparisons for all this data for 8 millions comparison, but we don't have this problem.
Yeah, but especially at high significant wave height, I think that the altimeter are very helpful, because there are very little buoy measurements, and the model are known to underestimate the significant wave height at high wave height.
And the buoy also.
Can I say something? I think you already mentioned that these kinds of algorithms are quite mighty of deriving those SeaSAR parameters. I would suggest, when you go through your last slide, I think you made some suggestion on where the future might lie on these algorithms. And you said that it's actually the neural network. And I have the impression that in this case, you actually use the neural networks as a placeholder when you want actually to say machine learning. Yeah, so I think you are already aware on this benefit of using this kind of techniques. But maybe you changed the statement from a neural network to machine learning to have it more general, including, for example, this algorithm here.
Yeah, machine instead of deep.
Okay.
But we need to show it now. I don't know how to. We are not showing this one.
Right. Current slide.
Yeah. This one.
It's not. Anywhere there is ML now.
What is a slide from this? I don't know.
Can I give a small comment?
You know what is the mouse? Yeah, for sure. Go ahead.
My opinion, we have two knowledge gap, and it is very important to take it for the future. If we all, at least how I know, train our function, we use all possible data without priority. We don't have any information on uncertainty from a sea state. It means if you, for example, have a model of a buoy in different areas worldwide, some areas you have more uncertainty, also differences between different models or buoy on some location. And you must, of course, you should for future make some map chart from the uncertainty worldwide for sea state, uncertainty in the ground truth data. So we can later by training to use some priority in what area with better to develop a model function. First and second point, we train all function, of course, for the sea state and without ice. So it's all in an area between 60 minus 60 degree. So, but of course we use it in a more than 60 degree, and my algorithm can distinguish between ice sea state algorithm, because one of the most important point in my algorithm is denoising and found out the artifacts. And if you have a small or large ice, it's no problem. But if your subsystem completely is under ice, it can be my algorithm cannot see the border, and you have in some, of course, to large values with sea state. So of course this is an error. So the problem is only per eye you can see, but we are working for an automatic processing. So it should be made automatically. We need more ground truth here, and we need to combine it sea state algorithm with better ice masking algorithm. Without ice masking algorithm, it is possible, but not automatically.
Yes, and on this aspect of CS masking, you see that the cutoff is really having a big difference in the ice-covered waters and the open water.
Yeah,
and
the problem is not with ice coverage. The problem is the boundary border between ice and sea state, maybe 500 meters. So now it is shorter than one long wavelength. No, it is only this border. The problem is this problem.
Okay, so now we have a question from Ben.
It means if you get I submitted this example image, but it's not included in this presentation. I process it if I process the sea state in partially covered ice. The ice itself, it's by my algorithms, it's cut it out. It's automatically found out, but with border between. So I have practically a border between sea state and ice. So some with higher sea state. It's not, of course, error.
So I hope you can present that in the breakout session on Wave, and then we can discuss more on this ice edge impact on the wave retrieval. So Ben, you have a question?
So I have three questions, or two questions and a comment. I'm trying to stay awake, so so bear with me. So have you ever anybody ever looked for microseisms, which are these standing waves that form from interaction? Kathleen wrote a nice paper with some people on that. And also, I've always wanted to see tsunami waves, and I don't think anybody's ever seen anything visually with SAR of a tsunami wave. I could be wrong. And the last thing is, you know, when you're looking at, and maybe I was sleeping in this when you were talking about waves and ice, but you know, it's important to understand what kind of ice it is. So if the wave problem in the ice is solved, well, what about distinguishing what kind of ice there is and using that in some combination product?
Yeah, so to start with your last comment, so far we have not been distinguishing which ice the wave are propagating in, but we know that it's propagating in break-up ice, but also in more rigid piece of ice sheet that have deformation because they are quite thin compared to the lens. And but for now we have not tried to estimate the ice type from the wave signal that we observe in ice. And so for the tsunami, in fact, there was a tsunami, not a tsunami, but like underwater volcano that create some kind of tsunami wave. And but at least very long swell wavelengths resulted from the tsunami, and it was spotted on the wave mode. So it was like a few kilometer wavelengths. So it's not the 600 kilometer wavelengths, but at least it's a signature of this underwater volcano or eruption. And so your first question was the microseism. There have been some attempt to combine the macroseism and the actual wave mode to triangulate to get the storm source, and in fact it proved to be very useful, very accurate, because the spectral resolution of the microseism analysis is quite good, because you have a quite long time series, and so this proved to be very efficient because the spectral resolution is very good. We are still there are still some unknown on the intensity, because apparently they are caused by a standing wave that are reflecting by the coast, because the propagating wave do not have a signal that propagate down in terms of microseism, and so it really depends on the shore type of coastline. Like if it's a cliff, you will have a strong reflection and the microseism will be large. And if you have a beach, for example, there will be little reflection, and so you will have much less microseism intensity. So to detect the origin of the storm, it's really efficient, but to estimate the intensity of the storm, it's still a question to develop more the interaction model for doing that.
It's coffee time. We have to break and we can't break for longer than 10 minutes. I'm going to chase you out there and get back to you.
Tell that to the online people as well. Yes, Johnny wasn't speaking into a microphone, so for the online people, it's a 10-minute break, and we'll be back. Hello, hello. Can I have your attention? Let's continue, move a bit upwards to the atmosphere, kind of, at least, and look at the near surface wind retrievals. It is the waves. So we have new chairs. Over to you. Is Johnny in the room? Yes. How much time do we have before dinner and drinks?
The introductory presentation, you have 45 minutes.
Yep.
And the question is whether we proceed with the questions. Another 20, 25, 30 minutes. Then go to the topics. If the audience are willing to join me in this, I would prefer to do it that way. Meaning that everything is delayed by an hour. Up to here until 7 o'clock. Then we go to the icebreaker.
So you have, if I understood correctly, you have 1 hour, 20 minutes. So it will be 7:10, and then the eating will commence. So up to you. Go ahead.
Okay. Without further ado, we'll move into the wind retrievals and detection of extremes, which were combined into one theme as we started to collect information from people for the meeting. I think we ended up having about 6 submissions of new material associated across these topics. And the speakers provided some of that material, and Roman did a nice job pulling everything together. So they're incorporated into some of the material that's going to be presented today. And I guess we'll try to run through this as quickly as we can. And I think that the idea for today is Roman is going to take the part about the surface wind and its retrievals. And then Ad is going to follow up with some thoughts about connecting SAR data with scatterometry. And I think that this session and theme should dovetail very well with what was just discussed on the wave side. The whole idea of the fact that most of the time we're measuring surface waves for everything we're doing bodes well for this idea of bringing the inversion of the currents and the waves and the winds together as a way to move forward. But without further ado, I think we'll get going.
Thank you, Doug. So I'm Romain Husson, and of course I would like to thank all the people that participated to this presentation, including the authors and co-authors that will be presenting during the breakout sessions. One thing that I was happy to do when I started to study SAR, wind and waves, that was in 2009 for my PhD, and I really liked right after this, the SeaSAR 2012 white paper by Knut Freud, because I think it provided a nice overview of what was done, what was the status of the fundamental relationship between SAR, observables, and wind, how we can retrieve the SAR, how it was applied at that time, and now we are added up that last part about connecting SAR and SCAT. And I try to use the same plan because I think it's a nice attempt to try to see what was added on top of what was done and published in 2012. And what you were saying, Doug, just right before, you were telling the fact that what people were saying in 2012 or in the beginning is that we were having with the wind data quite a mature product, and what we were lacking is mainly the lack of data. And now we see that now we have a lot more data, we have a lot better knowledge of the data, and we are looking for better data quality, so and more mature wind algorithms, so it's always bouncing back and forth. So the SAR can provide a wide variety of wind-related observables. There are many of them. The most used ones that everyone has been using since the beginning to retrieve the wind is mainly the co-polarized sigma naught, but also the cross-polarized lately after with the interest into the extreme winds. But there are also a lot of additional parameters that were already known, but also some new ones that have been added to that list. One of them is the co-cross-polarization coherence, following some work from Nicolas Longepé. But we've been talking already a little bit about the Doppler shift, and that will be part of the presentation in the dedicated teams. And there is also the IMAX, the mean cross spectra, which is following some work that were done in 2018. And we'll talk a little bit also about the wind streaks orientation, and there were two related presentations by Stefano Zecchetto and Robin Marquardt on this. So all these variables, they are also very interrelated with the other themes, the waves, the currents, Doppler shifts, retrieval, but also the ice. So as Fab and Marcel was saying before, there is a lot and higher interest to be able to have, let's say, this mirror retrieval where you kind of follow all the variables, all the parameters all together. And also some of these parameters, they can only be retrieved from a single look complex data, like the wave, the current Doppler, while some others are okay with the grand detection product. So there is an interest to start working globally on the single looks data overall for all these parameters. And also talking about the resolution, it's obvious that not all these parameters are available at the same resolution. Some of them are available at the rawest and highest resolution, like the sigma naught, down to 10 meters, but some others, like the IMAX, for instance, it's available at a much higher resolution, up to 10 kilometers. So it's raising a lot of questions on how can we mix all these SAR observables at different resolutions to try to retrieve the highest resolved wind information. So also some other issues that we have is that whenever we try to retrieve the wind, there's a lot of other stuff going on in the ocean. So there can be rain, sea ice, waves, whether it's swell, breakers, some currents, some oil slicks. And it can show also, if you look at the texture, some marine atmospheric boundary layer coherent structures. And all that also will be, of course, tackled in the other teams, methodology, thematics, sea ice, currents, waves. But what this is showing is that if you look at this image, you don't want to be extracting wind from that overall area. Otherwise, you would be having very much underestimated winds or very overestimated winds. So this is requiring some dedicated pre and post-processing steps, as for instance, the rain that can be seen here. You see some convection fronts also over here. You have some oil slicks if you look thinner, and some internal waves. So just to recall the variety of the processes that you can see on the SAR images. So this presentation will be given by Aurélien Collin in the thematic and methodology techniques. So the copolarized, just to look at the different SAR observables one by one. So the copolarized sigma node, so there's been many different families and updates of them, like for the cross-pole. So starting with, now we have mostly the CMOD 5N, which is very widely used, but also the CMOD 7. They are showing whenever compared to references, especially looking at, for instance, for the high winds, the SFMR wind speed. It can show some underestimates for the higher wind regime. So that's why the CMOD 70 was developed to be able to adapt to the drop zones. And this is now allowing a better agreement between the SAR and the SCAD for this particular copole. And now it's therefore showing less inconsistency, and you have the relevant publications beneath, and Ad will talk more about this aspect in the last part of this presentation. For the cross-pole, well, basically this polarization is particularly adapted to we know the higher wind regimes, starting from 15, 20 up to 80 meters per second. There have been many different cross-pole GMF, H14E, C2PO, MS1A, the same for high winds. And all these updates have been done because there is a strong sensitivity to many various aspects. So first of all, the size of the validation dataset, because it's hard to have large enough dataset over the extremes. The extremes are rare, and therefore it's hard to have a large enough dataset to build it. We'll talk later on about the shock initiative that Yves Louis has already recalled, that enabled gathering many Sentinel-1 observations of the tropical cyclones and developing this cross-polarized sigma node GMF. So the source reference is also quite scarce because it's not because you have a SAR image that you have a collocated source reference. So for this, the SFMR collocations were very useful, but before that there were SMAP and SMOS used as a reference. And also the SAR sensor requires to be rightly annotated and corrected, especially concerning the noise, which starts to be quite can be quite a limitation for the cross polarization because the signal to noise ratio is so much higher than in the copole. So there can be also some limitations and sensitivities to that aspect. Also, of course, non-wind phenomena like rain, for instance, which is much often detected present in the highest wind conditions, but potentially also less easily detected due to those fewer contrasts. And to be noted also is that this cross-pole was noted to be very well correlated with the L-band passive brightness temperature from SMOS, for instance. And there's been many publications on that, and it can be very helpful and give some future ideas also from future missions with combining L and C bands. So the co-cross-polarization coherence. So that parameter was first looked at with RadarSat data. And from this paper from Nicolas Longépé, it was using Sentinel-1 data, the dual-pole data. So what this is showing, this is basically showing the behavior of this parameter, which is combining the co and the cross-pole complex measurements. This is showing some, we have the well-known behavior of the VV sigma naught with respect to the relative wind direction, the one that we know from the co-pole, but the two other plots are showing the effect of the amplitude and the real part, because this is a complex signal with respect to that direction. And this is actually a very useful information that you can use at about a resolution of 10 kilometers. And it's very complementary to the Doppler, because the Doppler will have a different wind direction dependency, which makes these two variables very complementary to one another if you want to use them complementarily to retrieve the wind speed. What has been done before with this work is that the relation was extended to 14 meters per second because it requires a lot of work with respect to using complex data. And what is lacking maybe in the future is the fact of extending this relation to higher wind speeds and to see if it can be used for higher wind regimes. The Doppler shift, so there will be a lot of discussions about it, so I don't want to go much into details about that, but basically it's a very interesting signal because it can potentially, it does not saturate at extreme winds. You keep on having a very, very good relation between the Doppler shift and the wind speed, the radial wind speed. This information is only not so well calibrated for, let's say, the near real-time data. There's a lot of work to try to provide data that is well calibrated for the archive data, but also for the near real time, but still it's not available right now. And clearly this should be one of the main requirements for the potentially next mission, Sentinel-1 to make sure that we have a very good knowledge of that parameter. This information is available at about a resolution of 2 to 4 kilometers, and that's it. The wind streaks as a proxy for wind surface direction. I could have had a question mark. The wind streaks, whenever they are present, they give information on the approximate wind direction and also on the atmospheric stability. The orientation is close to the wind direction, but often not exactly the same one. It has a significant bias. Some authors indicate from model and measurements some 10-degree bias changing between North and South Hemisphere, like a publication from Foster 2005. And there can also be large differences in certain conditions, but still this is a useful information that makes it a way to have a wind direction estimate that is a measurement that you can really relate to your NRCS or to the other SAR observables. Because what we are doing now is we're using the a priori model as a proxy, as a deficiency of multi-look angle. There are many different techniques that were developed from Fourier transform, local gradients, continuous wavelets, ResNet. ResNet is mostly the one that is now showing the best results in the sense that it's providing the highest resolution and also giving some uncertainty at the same time. The interest is that for this exact reason, you can manage to have quite a high resolution of the wind direction with ResNet. And therefore, you can start to look at spatial characteristics of the marine atmospheric boundary layer, both for wind speed and direction at fine scales, not only the wind speed. So on the right, what you see are some extracted graph from Stefano Zecchetto abstract, where you see on the top the wind maps from ResNet and from the OCN product for two different cases. And you can see that if you consider this variation of direction, you add a lot more information in direction and speed to your product. So the wind streaks, it has been known since almost ERS 1 and 2 and before that you can see in the SAR images so this pattern, And now we look a bit more at the VH texture, and what we see now that we have also a lot more observations of the extremes is the fact that the VH brings a lot of information useful in the case of, for instance, tropical cyclones, because the VV texture can be more sensitive to coexisting long waves, and therefore what you're measuring is not the wind direction, not the wind streaks direction, but just the waves, which is not necessarily instantaneously related to your wind. So what we're seeing on the right corresponds to the winds streaks orientation estimated from for tropical cyclone Surigae, but I believe this is only for the VH. But still, the PV is quite useful. If you look at the error for VV in red and VH in blue, you will see that you have a very much good information for the strongest winds, but also a good information for the VV for the lowest wind. So there's a good complementarity in between the two that should be exploited. So it is of interest if you start looking at this wind direction. If you start looking, for instance, this is an example of some gradient method that were used to compare the SAR, VV, and VH, both with dropzone, ASCAT, and ECMWF. And what you see on this graph is the orientation estimated from the VV, from the VH, the dual signal, and ASCAT. And you see that whenever you combine the two in the dual, you have something that is much more, much closer to the ASCAT reference. Also, a little slide on the texture characteristic, which will be anyway more developed in the team methodology and techniques. Just to talk about the fact that on top of the orientation of your wind streak, you can look at additional features like the width of your wind streaks, but also the texture overall, because you can have wind streaks like you have here, like you have over here on the left, but you can have also some what's called micro-convection or transient state in between the two, and this is giving some information about the MABL characteristics. And also one very interesting fact is that you can relate the characteristic of your wind streaks with the Monin-Obukhov length, L, which is a very important parameter to look at the stability of the marine atmospheric boundary layer. So the IMAX was also already a little bit discussed in the previous presentation. There is, of course, a lot of interdependency between the instantaneous winds and the wind C that the IMAX is looking at. So this contains such a local wind signature, which is very complementary to the radar cross-section. What we are looking at here is the IMAX with respect to the radial wind speed. Basically, this can be somehow seen as an alternative to the Doppler without the issues of calibrating it well. And this is very useful information potentially for the wind retrieval also, but with a little bit of a reduced resolution. I think here we're talking about something like 5 kilometer resolution, or maybe 10. Different example of wind inversions. Some also aspect about available soft. Oh, so this is okay. This is the plan from the original paper from Knut Freud, but I will not go through all of them. I will stick to the first one. And there is also a link with the abstract from ID Einberg on operational wind retrieval using cross-pole and Doppler data. So the dual pole wind inversion. So now that you have all these different SAR observables, you can try to mix them up to manage to have a wind inversion that's working well, both in the, let's say, normal wind conditions below 20 meters per second and up to the very high wind regimes. And this is now well developed and published, and it has been proving its very good efficiency for providing wind maps for tropical cyclones. So high resolution wind maps that can be used at 1 kilometer, but also downgraded resolutions to compare with small sense map radiometers. So there are several publications, for instance, from Mouche 2017 or 19. But also on top of that, what you can do is that, and we'll maybe talk a little bit more about this in the applications, is that you can also retrieve some additional parameters once you have these maps, like the radii, so the distance of maximum wind speed, and that distance in the different quadrants, and also for different threshold wind speeds. And this is showing very good agreements with the SFMR reference that's being used for such type of wind regimes. So if you start combining the different SAR observables, so right now in the publications, there are mostly some combinations between the code, the cross-pol. The Doppler is not really so used right now, but for calibration issues. But there are many different other information that can be used here. This is just to illustrate the fact in this, let's say, projection as a cost function. So what we are seeing on the bottom corresponds to U and V between 15, minus and plus 15. And what you are seeing is a cost function for the contribution that comes from the copol, which you see is not omnidirectional because it's an ellipse, not a round. So it gives you a probability of being in that direction. And as you can see, if you only use the copol, you will have an issue in finding the right direction. So that's why you are using the model that tells you that with a given error, you can alleviate the wind direction ambiguity, and you end up with this cost function that you minimize and gives you the speed and direction. But if you start to add more SAR observables, maybe you can also start to not even consider the model anymore. So this is illustrating the complementarity of the polarimetric GMF. So if you are using the CCPC, the cross polarization ratio, coherence, sorry. So this is giving you a good information for the azimuthal direction with respect to the Doppler that's giving you a good information in the opposite direction. And therefore, if you combine these two, you get a cost function that is already very well depicting the possible wind direction and speed without even having to use the model. So that gives you more independence with respect to the model. And then you can even start to look at residual for this cost function. And such type of residual in the minimized cost function could be used as additional quality flags that are data-based. Because we know that, for instance, rain impact can be quite an issue in the presence of, in the case of tropical cyclones, for instance, there are some large examples of attenuation or amplifications. Here we have an example of several dBs of impact because of heavy rain. So here this is measured given by a courtesy of William Perry for VV and VH in RadarSat-2, where we see the colocalized GPM rain rate. And we see that for very intense rain rate, we will have such type of attenuation. And how this can be filtered out is also presented in the method and techniques talk. If we move to the some examples, which are not exhaustive, of the operational implementations or processes of an understanding of the wind inversion, there are different examples that can be quoted. There's the Australian coastal SAR ocean winds, the portal that was presented by Salman Khan with his associated abstract. There will be Stoffelen that will talk about the connection between SAR and scatterometers in the section 4, and we'll look at the other extremes. And also there's a lot of applications, weather predictions for some examples of assimilation in numerical weather models. And one aspect, last aspect, but not the least, that is really getting a lot of interest right now is the application in the offshore wind farms. And that is making me link it to the presentation from Dimitriadou. Sorry, I forgot your first name. Crystal Dimitriadou. and the application to the Mediterranean Sea. So one example for this aspect is the fact that for the Australian portal, we have tried to augment the scatterometer global wind that were available in that area, but to add up the high resolution information from the SeaSAR, Sentinel-1 currently. And how that was done is that we have started to, by calibrating and validating the level 2 Sentinel-1 data. So they start from the level 2, they calibrated with respect to method A and B, and they are making this product available on that portal. You can see the comparisons between the two wind speed on the right side, with the cuckoo plots that showing a little bit of a difference for the higher wind regimes and for the lower ones, but there are some questions with respect to the use of cross-pole and well, here the cross-pole is not used, sorry, but with the fact that there can be some bias for the higher wind speed, and the resolution, I think, is also playing a role, yes. 1 kilometer, I believe. But it's the fact that maybe the resolution is different between the SCAT and the SAR is showing a lot of, indicating a lot of difference in the bias. I'm not sure whether they degrade the resolution to the same level when they do these comparisons. So I don't know, Salman, if you're hearing at us, that would be a question to you.
Which CMOD is it? CMOD 7 or?
This one is the CMOD 5N. Yeah. One additional application, which is more tropical cyclone based. There are now many different initiatives. It started originally with the Canadian, actually, with their Hurricane Watch program with RadarSat-2 that started to look a lot and make some acquisitions of other tropical cyclones. And this is now enriched with RCM, the constellation of 3 satellites that are almost systematically making some acquisitions of other tropical cyclones. And with RadarSat-2, this is what gives us the idea of trying to develop the same kind of triggering of other tropical cyclones. So this is the SHOCK campaign, let's say, that started in 2016 with Yves Louis. So the idea is that over the tropical cyclone regions, the satellite is not acquiring any data or not in the right mode. So what you want to do is to, because you know the forecast of your tropical cyclones a few days ahead, here that's shown in white with a bit of a certainty around the center, you may want to be able to task some acquisitions, so late programming acquisitions along that forecast track. And if you can do that, then you have a lot of chances to catch the hurricane eye. And we can see now when we have a little bit more of a feedback and analysis on that exercise that we have chances of acquiring in 50% of the cases the eye. We can catch it very often if we task it 1 day in advance. And it goes down to 10% chances if we task it 5 days in advance, because the tropical cyclone forecast track has a lot of uncertainty after too much time. And so now an example of it, there are 2 main, let's say, implementations of that process. One for the Cyclops and EODA platform for the archive and NRT in collaboration with ESA, and another one made by the NOAA. And they are making this specifically wind processing that are using the dual pole, so not the copole, the casual processing that is being delivered in the level 2 OCN by ESA. It's being available, and it's been now widely used by the WMO tropical cyclone forecasters, and there are already quite some publications about the usefulness of this data. And the main gap that is identified now is the fact that an intercalibration between the different sensors is needed, because they may not have all the same way to calibrate their sensors, not the same strategies, but in the end, you still want to have the same wind if you have the same conditions, whatever the sensor. Also, an additional issue that they have several times iteratively given is the fact that rain was an issue, and they need to know whether some kind of contamination from the rain is present or not. So there is a little bit of work on that aspect, and it will be discussed during the method session. And here this is just illustrating what was shown before, all the acquisitions that could be performed for tropical cyclone Freddy. Once you start to have wind observations over the extremes, you can look at different extremes, not only the tropical cyclones, but also polar lows, Medicaid extratropical cyclones. The polar low example is very interesting because it's a very tiny phenomenon. So to be able to use the wide coverage and the high resolution from the SAR makes it a very unique sensor. Plus, you have the high frequency revisits over the higher latitudes, which gives you a better observations. So you can really follow your systems in a better way, and you just have to make sure that you remove the sea ice, as was indicated in the previous work, previous team by DLR. And if you start looking at if you extract the local wind direction and you combine, in this case, not only the VV, VH, but also potentially the HHHV, due to the fact that in different areas you have different polarizations. So you need to use a polarization ratio. So a bit more of additional algorithms, additional steps. Then you can start to locate your center, but also identify the same type of information, the higher wind speed, and all this structure that can be given. What we see on the left, sorry, is a polar low example, courtesy of William Perry. And on the right side, what you see corresponds to all the polar lows that were extracted from the Rojo 2019 publications, where they make an archive of all the polar lows, and that was collocated with the SAR catalog, and the collocated SAR with polar lows were processed, and this is what is shown. You have quite a lot of systems that are available, including nearby Svalbard. You also have other phenomena of interest, so extratropical cyclones, medicanes. What we see on the bottom is an example of what happened in 2021 in October, where we had this medicane called Blas that caused very heavy rainfall and some intense winds. Not as intense as for the most intense tropical cyclones, but still can be quite devastating. And in this case, even the rain is more damaging than the winds. So maybe one comment that can be done is that for these systems, for the tropical cyclones monitoring, there are now almost 7 satellites of SAR that are systematically imaging these phenomena. But as on the opposite, what happens in the mid-latitude for such phenomena, there is a lot less acquisitions. So it would be useful, for instance, if we could have some contributing missions that could help also targeting at such events to try to better follow and monitor them, as what is being done for the tropical cyclones. So the applications in the different topic for the offshore wind farm. So basically, there's been a lot of growing interest for using the SAR to try to have a high description of your wind in the coastal area, because of the resolution of the SAR can provide with respect to the other scatterometers, for instance, even though the offshore wind farm are moving further and further away from the coast. But basically now there is quite a huge 20-year archive of Sentinel-1 and VSAT acquisitions with major sampling of Europe, and the wind resource assessment based on remote sensing is not so straightforward, because something that you would need to be able to use such an archive is to have a very homogeneous catalog of this data to make sure that the quality of the data is homogeneous in time, because a very tiny variation of your wind speed can have a very large impact in terms of produced energy, due to the fact that the energy is proportional to V power 3. So a lot of impact potentially, and they need also to be intercalibrated between Sentinel-1 and VSAT. So this is really requiring a lot of work, and you can see also that not only between the ASCAT and SAR, here we see some differences that are of the order of, let's say, between 0 and 1 meter per second in that area, but also potentially only considering the SAR image on the bottom. So here what we are seeing is the Weibull power density. So basically this is a proxy that is used to estimate the downstream annual energy production. And you can see also some artifacts that are due to the fact that you have potentially different performances depending on the incidence angles, or also depending on the density of observations. So there are several aspects that need to be taken into account to provide the most precise wind regime, mean wind. So there has been several publications about this. Also, the fact that the SAR measurements can not only provide the wind measurement at the surface, but also potentially at hub height. So this is some work that was proposed by Badger in 2016 and Montera in 2022. Basically, if you used information from the model about the stratification of your atmospheric boundary layer, you can infer what the wind speed is going to be at hub height, so about 120, 40, 50 meters, thanks to the information that's provided by a model, and this is working quite well. And where, for the matter of wind resource assessments, this is requiring the most accurate winds in the range of 3 to 12 meters per second. And this is due to the fact that to the turbine power curves, because the turbines, they basically start producing electricity at 3 meters. And after 11, 12 meters per second, then it's maximum energy that's being produced. So whatever is your estimation, it's same impact. So this really is where you need to be very accurate for your wind estimate. So this is requiring an extensive knowledge and correction of your SAR-derived winds and potential impact of the incidence angle of the antenna patterns that may be not well known, modelized, or can have a huge impact. And potentially, still, the SAR is giving quite a good, let's say, overall picture and spatial distribution. And that spatial distribution, the accuracy can be improved with some local truth to avoid, for instance, multiple in situ campaign. So that will be further presented by Cristalia with example of the Gulf of Lion with a current which is a current hotspot. Also very interesting for the SAR application because it's very complex topography with very various local wind regimes. And now I will leave the floor to Ad, which I think is connected with us.
You hear me?
Or do you want to make questions first on this first part? Or in the end? Okay. We hear you well, Ad.
Okay, very good. You can turn the slides or?
Yeah, I can. Okay.
Okay, then good afternoon or good evening, even everybody. I will talk about the usefulness for SAR actually for spectrometer winds and also vice versa. So of course we have to look at what Romain already explained, the different objectives that we have for spectrometers and SAR. So for SAR we want to have kilometer scale wind vectors. We look at mesoscale wind structures. We want to look at structures of extremes. And there's many innovations that Romain went through, so I don't think I have to repeat this. For instance, he mentioned that for hurricanes, the SAR data are very useful to get the radii of the hurricane bands of high and extreme winds. So that, of course, is of course very useful. So next slide. Yes. So there are knowledge gaps on the kilometer scale wind vectors. Also, Romain talked about that, which is to get both speed and direction remains a weak point. So I will talk a little bit about accuracy. And calibration is also an issue that is not much discussed, but is really an issue, for instance, at low winds in particular. So to get good winds, you need a calibrated radial cross-section down to 0.1 dB. If you want to get high quality 1 kilometer scale winds by a 3-view SAR. So this is something you can derive from what we know about wind retrieval from spectrometers, what we know about 3D turbulence spectra in the atmosphere, how they decay with wavelength, with wave number. So the smaller the scales, the more accuracy you need to be able to distinguish these small scales. And of course, the calibration is then important to distinguish between calibration artifacts and smaller scales, but also to understand what is the real level of the winds. Outlook and recommendations, I think for SAR is really that the usefulness is very well demonstrated. So we would like to make the SAR winds a constellation and operational. Compare operational products for consolidation and to motivate standardization for user convenience. This is also something that we want to do for spectrometers in the CGMS Ocean Surface Wind Task Group, because users, of course, they do not understand all the different products and they really would like to have one look and feel if possible. And to do that is actually a lot of work to compare all the different instruments and to make sure that they are intercalibrated. So one thing to do, which is useful, is to verify the consistency with spectrometers on the 20 kilometer scale, because there we now have 7 operational spectrometers. We intercalibrate them, and I will show some results to try and convince you that we know very well what we are doing. But also we should compare maybe more with Hurricane Hunter underflights. In particular, they have a new rain and wind instrument called IRAP, which actually profiles the rain above the sea and also gets the surface return. So it is a very interesting instrument to understand the variability at the surface, but also in the atmosphere above. And I think that's very useful to compare to the SAR. The last point is very important. Really, we need an extreme in situ wind speed reference for all satellite wind calibration. So for any satellite instrument, we do not have an absolute wind speed calibration. There's no physics that can tell us what the absolute calibration is. So to calibrate these satellite instruments, we really need in situ wind speed references. And we've been using moored buoys, particularly at ECMF and for ASCAT calibration in the EUMETSAT SAF. But in extremes, instruments have been calibrated with drop zones. And there's really a lot of documentation now that there is really a large discrepancy between drop zone calibration and moored buoy calibration, particularly in regime where both can be used for calibration, which is between 20 and 25 meters per second. And at 25 meters per second, the errors are really huge. So that explains all the plots you've seen about the saturation of copole winds. It's not a we can correct that, as you've seen, by just rescaling the winds, and we get good winds from ASCAT up to 50 meters per second without any problem. So it's very important that we do this calibration and that we have a reference not only for the hurricane community, they can live with what they have, drop zones, but if you want to understand the physics, how many air molecules are hitting the water surface, then you really need to know what is the real wind at the surface. And currently we have a large uncertainty in that. The next slide. Next slide.
Yeah, just a question from Craig.
Yeah, it's thanks for those comments. I mean, on this whole business of high wind speeds, I mean, you know, when we're talking about the sea surface at very high wind speeds, there isn't much of a sea surface left. The waves are blown apart. There's spume going everywhere, and so the very characteristics of the sea surface are no longer intuitive for a SAR and a scatterometer. So I think the absolute reference for winds, you know, it's a fundamental physical change at the ocean surface that is going to confound us. And I'm not sure that we're on top of that just yet. But clearly, when you're in those winds, if I've been, and several others, there isn't a sea surface anymore. It's just a white mass of stuff.
Well, I've been there, Greg. You know that.
Me too.
I must say I somehow disagree with you, and that's also what we see in the data. In the data, we see that we can actually get these winds ready from SAR, both in the copole and crosspole. Of course, for copole, we know that the sensitivity is decreasing, but it implies that if you have enough accuracy, you can still get a reasonable wind. What the wind really is down there is, of course, a very difficult physical problem. So from that point of view, I do agree, not only for the surface, but also for the 10-meter wind, of course, because it's, of course, moderated by the waves and it goes everywhere. But still, the hurricane strength is measured in terms of 1 minute sustained winds, and that is because that is what's causing the damage. So I don't think we should try and get away from it. We should try and resolve this issue and see what problems we encounter while doing it. And for the moment, I can only say I'm only becoming more optimistic of how far we can push this. So when I started scatterometry, in fact, in 1987, they told me, forget scatterometry above 20 meters per second. And today I say, well, we can do it at 50. So I think we should push it further. Yes, so of course, we need the SAR for the details, particular extremes, but also for coastal and for air-sea interaction. And this is also very useful for scatterometers because then we actually, for instance, for coastal processing, we use the SAR to verify whether we get artifacts in the coastal processing of scatterometers that we can see in the SAR. And you can see beaches in the SAR, we can see all kinds of things that could actually contaminate our wind retrievals of scatterometers near the coast. But of course, winds near the coast of all these 7 scatterometers is something that is really needed for a lot of applications. SAR cannot capture the temporal variability of the atmosphere. There's just too little data to get a 4D view of the atmosphere, so that is not possible. For scatterometers, it's already difficult, and for models, it's even more difficult to follow the convection in the atmosphere. The SAR are also not well calibrated with respect to the scatterometers, so we are doing, of course, scatterometer intercalibration, which is a heavy task, I should say. But we are now able to intercalibrate KU bands, C bands, different types of scatterometers by providing an NRCS that is giving the same winds using the geophysical model functions that we have learned from data science. We also want to limit the problem that different producers generate wind products with different characteristics. So next week there will be the CGMS International Winds Working Group, and one of the aims there is to try to get these wind products that have the same look and feel so that users can easily use them whether they're from one producer or the other. This is really very important for, let's say, operational applications. So scatterometers show much more detail of physical weather processes than global NLP models do. We have a large virtual constellation. Scatterometers are very stable and well calibrated. So we have NRCS and wind errors that are well known. and quite low as compared to in situ data and model data. We use the same geophysical model function, so we are successful in calibrating the NRCS by changing the level 0 processing and keeping the wind processing the same. So that is good news, of course. And we use very similar retrievals for very different instruments. Yes, next slide. So we have some knowledge by what I called here cone data science. So in the spectrometer you have, with ASCAT we have 3 antennas, and they make that we can see the ocean surface with 3 views at the same, almost the same time, and quite a large footprint, as you know. We looked at these cones for ERES and ASCAT, and we can make them match. So we can use them for calibration. The cone is something that should stay the same. It's a, let's say, a physical signature that the data provides you, and you can learn from it. So the cone should not change over time. So you can do relative beam pattern calibration, and we found out this can be done down to a few hundredths of a dB. In the smaller plot below, you can see how you can use it for noise assessment. So you can see how the 3 views actually differ in terms of the mean that you would expect. So we can also use it for GMF development because we can try to fit the surface. We can see rain at different points than wind, and therefore we can do the quality control using this type of surface. We are now trying to also see how much we can push satellite pointing to see whether we can see movements of the cone when the satellite pointing is changing. But this is work that has to be done. But the whole scheme actually tells us that the spectrometer is dependent on 2 parameters. We can make GMFs that fit the cone down to a tenth of a dB, which is about a tenth of a meter per second. So that gives you good accuracy winds in principle. We are developing now a CMOD 8 that is purely cone based, so that can go even better, we think. We compute of every point the distance to the surface, and that is what we call MLE, and we know that the MLE is associated with sub-wind vector cell wind variability. And for spectrometer, this is likely due to the footprint mismatches. So it has the right size, and yes. So the amplitude parameter, so the thing along the cone, matches closely with wind speed over the wind vector cell. And this is so irrespective of the long waves. So this is dependent on the state in the 25-kilometer wind vector cell. Direction as described by a double harmonic is the opening of the cone, and that verifies very closely with wind direction of buoys. And then we, of course, make a lot of different analysis, scatter plots, and she suggests that the differences are mainly due to wind variability. The 3D wind turbulence, and that is giving us a spatial representation error in triple collocation. And of course, we can use these findings that we have and compare it to what we get with 20-kilometer SeaSAR, because of course the spectrometer data is global based on a lot of statistics, and SeaSAR is more local, but of course it should keep the consistency also locally. So that is something we can exploit also in SeaSAR development. Next slide. Just to give some examples of errors that we compute for spectrometers. So here you see the U and V errors for all triple collocation data. And these are sets where we have different triple collocation data sets with buoys, ASCAT and SCATSAT, buoys, ASCAT and ECMF, buoys, SCATSAT, ECMF, ASCAT, SCATSAT, ECMF. So all different triple collocation data sets, and then we compute these errors, and they are very similar. They're all the same. We also have a paper on quintuple collocation analysis where we can also do, where we actually theoretically can compute the errors, and that's all very consistent. You see that the buoy error is so the ASCAT errors are like 0.4 meter per second, but you see that the buoy errors are larger. The buoy error is, of course, not the measurement error of the buoy because that's very low, but actually the buoy error is the spatial variance within the spectrometer wind vector cell. And that's the variance that a SAR should then resolve within these within the wind vector cell. Is of that size. That's the let's say additional structure that you would expect from the wind. So next slide. Yes. So we would like to connect winds, of course, to what happens in the atmosphere. So we also compute spatial derivatives. And here you see a log plot where we a log plot against divergence. Sorry. On the left-hand side, you see extreme convergence. On the right-hand side, you see extreme divergence. And in the middle, you see the main PDF. The green line is collocated data from ECF. So you see that the green line actually is not containing the extremes that ASCAT is seeing. So ASCAT has these heavy tails and ECF has Gaussian tails. Greg King did work to show that these extreme convergences and divergences in the tropical area are associated to rain. So rain is measured, for instance, by the GBM, of course, or by major static generation. Then you have an image every 15 minutes, and we use that to see when convergence, extreme convergence happens and when extreme divergence happens. And then it turns out that extreme convergence is happening about 15 minutes before the heavy precipitation, and extreme divergence is happening about 15 minutes after the heavy precipitation. So we can compare it with MSG precipitation loops. So it seems that these extremes are really connected to the moist convection, as we also see in the plots, of course. This implies that ECF is not showing these downdrafts and updrafts, these extremes, which of course has quite some implications for RC interaction, because moist air is going up and dry, cold air is coming down. So that is changing the whole scene for RC fluxes. So next slide. This is just showing method B and C. And on the top, you see above the text, you see that they actually overlap. So method B and method C have the same coverage. It's only separated by 50 minutes. So then on the right-hand side, we actually computed the mean divergence and the standard deviation over a given period. And when you compare the two plots, you see that the variability patterns are the same, but you also see that the detailed structures are actually different. So this implies that the extreme convergences and divergences are actually changing in 50 minutes. And that's also what we see in the spectrometer data. So if we want to look at these small scales and we want to follow them in time, we need a very high temporal resolution, in fact. You also see that the large divergences actually associate very well with large SST gradients, which is something we also expect. So of course, the coupling to the sea state is also very obvious in these type of plots. If we look at global models, and that's something I will show next, then we do not see this variability. As I said, we already miss the extreme, but we also miss variability. So next slide. So this is about the ESA-Max SS project on extremes. So intercalibration of winds from different satellites for nowcasting user convenience, of course. So we were very happy with the Cyclops database and the SAR winds, collocate them with ASCAT, and then we can try to use 2D VAR for resolution enhancement of C and KU band spectrometers. And then for an earlier project at EUMETSAT called CHEFS, there we looked at the effect of using stress equivalent winds in hurricanes, which is substantial. So we should use stress equivalent winds for wind retrievals over the ocean. not only in hurricanes, in fact, that's in the Clue AL. We work in the whole team, including also Marcos on, in particular Marcos, on intercalibration and geophysical model function development of all these different spectrometers. Develop coastal spectrometer winds, and that is, as I said, informed by SAR collocations. We exploit, of course, the C-band crosspol on SCA, and that is also informed by SAR GMFs. And then we do error assessments, of course, of the in-situ spectrometer and model biases. This is also relevant for SAR. We find that the general monthly local model biases are in fact larger and hence more important than the sub-25 kilometer scale wind variability. So we could say we have an elephant in the room if we want to look at small scales in terms of informing models. These models have already problems that are on scales larger than 25 kilometers. So next slide. So this is giving an overview of the same points just to say where we are. So we've come a long way in intercalibration. We come a long way in exploiting SAR winds for resolution enhancement of C-band spectrometers, but not done it yet for KU band. If you look at the marine wind services, we are working on the coastal winds, so that's work in progress. We just released ASCAT spectrometer coastal winds in our processing, but not for KU band, that's ongoing. We use always ECMF and buoy stress equivalent winds in our SAF, but not in other publications. You still see that air mass density or air stability effects are mingled with other effects that determine differences. So then it's getting more complicated to understand what's going on. Also, spectrometer NRCS calibration is being done in the SAF. We also then change GMFs and work on quality control and rain. And this is all connected, of course, because if you take out rain, you, of course, somehow change your calibration and your GMF, and you have to redo it if everything is based on data science. So this is what is continuously happening. Yes, next slide. Go a bit more in detail. So this is just one example for resolution enhancement that we do in MaxSS. So on the right-hand side, you see at the top a SAR image, and at the bottom you see what we call enhanced ASCAT, which is actually a 2D VAR analysis based on resolution enhancement with ASCAT data as input and ECMF model field as input. And that works to give us more structure in hurricanes, as you can see. Next slide. So remaining knowledge gaps was the other question. That's the intercalibration of satellite winds, which all exclude calibration. And we need this in-situ wind speed reference to really better understand, a better wind in-situ reference to better understand the calibration of satellites. That's very clear. It also is, of course, important for model development because if the winds change, the drag changes, and therefore the model physics changes. So this absolute knowledge is quite relevant physically. Yes, the SAR winds are used for resolution enhancement of KU bands, or will be used for resolution enhancement for KU band spectrometers. Is our plan. So that is also still not done. Yes, and then for SAR level 2, level 3, level 4 spectrometer winds, we have worked on KU band rain detection, but now we have to do rain correction. That is in progress. And we exploit SAR to develop coastal spectrometer winds for more spectrometer instruments. We use, in the first point, we of course also use SAR for the rain detection because we can see this rain in the SAR image, but less obviously in the spectrometer. So that's why we can use it for validation. Yes, we work on the CMOD 8, as I said. And one important thing is the understanding of the origin of the large model biases that we see, because models are used by users, and if they are in error, then we get problems in ARC forcing, and we have problems in data assimilation, and we still have to work on solving these problems. And of course, solving this problem is also important if you want to look at smaller scales and parameterizations, because the errors are actually caused by parameterizations. Okay, next slide. Recommendations and outlook, of course, follows from the knowledge gaps, which is again the wind speed reference, the better exploitation of all the hurricane data we have, but also coastal data for SeaSAR. So we recommend to keep doing this, work on coastal rain, work on the improvement of the models, and there we need a combination, I think, of spectrometers and SeaSAR to understand what's going on at the surface, and maybe also other data to understand what's going up higher in the atmosphere, because the biases are obviously not only caused by the surface parameterizations, but also by dynamical closure and other things in the model. Yes, besides these further applications of spectrometer winds, new ocean scale missions will be needed to better understand and validate the dynamics at the ARC interface, and these are ongoing, and there will be presentations about this. So I think that recommendation is also very clear. Okay, next slide. This slide is to illustrate what we currently know about these biases. So this is wind speed bias of spectrometer minus NWP. This is over a month. And the scale is from -1 in blue to +1 in red. So we talk about something like a meter per second. In the tropics, typical difference between a spectrometer and a model is actually a meter per second. So you can see that if the model confuses a bias with structure, then it's not able to effectively assimilate the spectrometer data. And yeah, we believe that this is the case at the moment, that the biases actually prevent a good use of the data in data assimilation. But of course, if you push the ocean in the direction that is wrong with the wrong amplitude, there's also a problem. So also for ocean forcing, there is of course a problem if these model biases are so large. So we have here 5 spectrometers. So we have HCAT-B, HCAT-C. They measure at almost the same time as same place and time, as I said. 50 minutes difference. So the biases that we get are very similar in terms of difference. At the bottom you have Haiyang-B, which is at 6 in the morning and 6 in the evening. HCAT is 9:30 evening and morning. And then we have Haiyang-2C. This is a regressing satellite, so it has all times of day in it, and also Haiyang-D is regressing, but it's opposite, so it's actually measuring where C is not measuring. And you see that all these biases over this month are almost the same. And then at the top right, you see a plot where we subtract the HCAT-B bias from the Haiyang-2B bias. And you see that there is some structure in it, and that of course can also be diurnal structure because the time difference is a few hours. So next slide. This is the direction of the spectrometer, spectrometer minus NWP. And here the scale is from -6 to +6. And here you see these hemispheric biases. We've verified, obviously, with buoys, as I said. So these biases are really model biases, and they exist already for a long time. I already knew about them when I worked at ICMF in '94. So that's a long time ago. Again, all the spectrometers show the same thing, buoys show the same thing, and again, you make a difference, and you see that the difference, that the signal gets much lower. So you can correct it. Next slide.
I think I need to tell you that people are getting eager to discuss a little bit and move on to the tapas.
Yes, of course. I think I'm almost there.
Okay. Can you try to wrap it up?
Yes.
It's
so
just
this-
two last slides, but
Yes, yes. So this slide is again showing the meridional bias, and here you again see the difference between an experiment where the data is used, which is in operations, that is ASCAT B minus ECMF ops on the left, and on the right at the top, on the middle you have the an experiment when ASCAT is not used. You see the biases do not change much. And in fact, at the bottom row, you see indeed that the differences are not very big. So the biases are not corrected by ASCAT because the model dynamics and the parameterizations have their, let's say, their own dynamical balance, and they go back to it very quickly after the scatterometer data has been used. And that was really my last point. So, and the next slide is the other component, the zonal component, and there you see the same thing. So yeah, we really have a model issue which is relatively big compared to the structures we're going to measure in the wind by a SeaSAR. Also, of course, the structures that we measure with a spectrometer, and we are now looking for ways to correct these biases empirically in the model and see the effect in data assimilation and see the effect in ocean forcing, and that's work to do.
Thank you, Ed.
Yes, thanks.
We may have time for a few questions before we go eating.
We have
What?
we have time. We push the food a bit further so you can 15-20 minutes discussion.
Oh, sorry. Thank you, Ed. I have a question related to your, I think, 10 slides before. Go back to the slow, three more. Yes, next one. Yes, the last sentence. Do you give more, more details on because it seems to me like it's really correlated errors in RC coupling and observed model bias. It's really correlated. So how do you? Well, I didn't get the point on this last point on last sentence you mentioned here.
So, yeah, so we, as I said, we are sure that these are model biases.
Right, but it's really
they appear in buoys in situ data, and they appear in spectrometers. They appear in all the data that we see. We see the same biases in speed, direction, and components. And of course, you know that some of it is related to ocean current. That's only a small part of it. Huh? A small part of it is related to the fact that the spectrometer is measuring relative to the ocean surface, and the ECMF model is winds that are with respect to the fixed Earth. And this has been already documented beginning of the century against buoys that also have current measurements. And then you can see that you can take away a small part of it in terms of this.
But it's more Flex's problem with the models, which is producing biases, and this is really linked to the RC coupling.
Yes. Yeah, but you know, of course, that if the wind speed and the wind direction are wrong, then the fluxes will be wrong too. Yes.
There is dependency on directionality. Yeah.
Yes. Yeah. So of course it's a couple problem. I'm not, of course, not. We should do the full couple problem. Yes. And I think we have now the data to start with correcting the speeds and directions.
Yeah.
We have spatial data from spectrometers. We can compute the biases, and we can correct them, and we can check what the effects are. So is the effect indeed that data assimilation is much more effective if we remove the biases, which is what we expect? Is it also true that if we correct the ocean forcing, that the ocean forcing is changing the ocean? We know yes, but how much? That's not what we know. And what aspects? So I think we should test this because we know there is an error. And I think we should try to propagate the error and understand what it's doing.
Okay. The second question is more related to the wind retrieval on SAR side and also on the scatterometers. We have observed maybe a few years ago that there is a long swell dependency on the wind speed from scatterometers and also from the SAR without including tropical cyclones. It's more related to coastal area for a high resolution. Did you see such same things in your validation, Romain, or add for? Is there any long swell dependency for the wind retrieval?
Yeah, we tested this, of course, by comparing two models. But you're now referring to coastal effects. We did not test, of course, coastal effects because we did not go very close to the coast. We can only do that since 2 years now. So I think it's very interesting to of course further look at this at coastal effects. That's one of the recommendations effect. And also the coastal sea state, of course, is important in that respect too. In the open ocean, we investigated with model data. They are good enough to tell us what the fetch is, we think. And then we don't see this effect. We did recently a study with buoys, and then we see some effects, but it appears the effects are due to the buoys rather than due to the scatometer. But that is something we need to further explore, I think.
So just to re-mention what you were saying, you just mentioning the fact that there's a long swell dependency. Could be a swell direction or just the presence of swell in the wind retrieval. This is something we have looked at. Actually, looking at buoys to buoys, it's a bit difficult to assess precisely because it's very local, and you don't necessarily know whether you're looking at a local effect or whether you're looking at the presence of swell.
Yeah.
So nothing definite, and it's a minor contribution, of course, with respect to the known ones.
But couldn't this be more systematically explored in the SAR? Or is the wind behaving in a region where you have a good imaging of swell?
We have lots of SAR data. I'm sure there is a way that this can be quantified.
As I mentioned, in the frame of CFOSAT, we have seen this a few years ago when we checked NWP model output of the wind speed and the wave model collocation, and we have seen that for long swell we have biases in the wind speed, so in the scatterometers.
Mm-hmm.
So this is why I'm asking the question. So
yes, but that is
at the global scale. At the global scale.
Yes. That's a very dangerous assessment because the problem is that sea state depends on everything, also on speed-dependent biases. So if the model does not have the same speed reference as the scatometer, you would tend to see sea state-dependent biases. You will first have to do the calibration before you can do the dependency on ancillary data, because everything depends on everything.
Okay, we can bring that one into the breakout group. Question up in the back.
Yeah, you have mentioned some institute data. I was just wondering, have you considered collecting data from ships? Because technically it's possible to incorporate some of the wind data into the AIS message, and then you would have a lot of kind of ground truth data from the wind. And the second question is that when you mention different wind products, I wonder what kind of users do you have in mind? Are those all kind of climate modelers? Or you also consider, for example, those who develop wind-assisted propulsion ships and etc. And if so, if this user domain, which wind products would you recommend to use if somebody is looking into, wind-assisted propulsion?
For your
Not sure if it's clear.
For the first question, so about the reference for the wind, I think we already have enough trouble to manage to find a good reference talking about good, well-calibrated and well-known buoys and drop zones. And I think adding up in that the ship measurements will only add a little bit more of a hassle to try to make everything connect.
But there is ship measurements put together by Barasa, that you could look at. We could talk offline about what's already out there, and maybe you could start there.
Okay.
Yeah.
And in terms of the products and the recommendations on that side, I suppose the SAR coastal work, the group from Australia provided a really nice demonstration of kind of trying to push something for their MEDOPS down there. There's a broad spectrum, and I think we'll try to capture some of that this week. So again, maybe we can talk offline a little bit about that too.
Okay. Yeah. Thank you.
Yeah, maybe one thing I like to add, which is the CGMS group that I mentioned, which is trying to standardize wind products, but also in the International Wind Sparking Group for meteorological users, but also the products are generally used by models, by nowcasters, by meteorological service providers. So there's a very big operational community for winds, and this community actually would prefer to have standardized products. And of course, it's up to us as this community too, the SeaSAR, to make sure that we can provide such products with, let's say, quantified quality levels.
Add on your comparisons of the scatterometer to the numerical model had very particular spatial patterns associated with it, and you were attributing, I think, the difference mainly to model error as opposed to scatterometer error. Is that correct?
That's what we find through our triple collocations. Yes.
Okay, so
yeah.
my question is then, does that indicate to you whether or not there's an excess or a deficit of downward momentum transport through the boundary layer from the upper level winds, or is there a difference spatially between one region of the model having an excess of momentum transfer down or a deficit of momentum transfer downwards, starting from the wind above the boundary layer?
That is, I think, work to be done. So if you can read it from the plots that I've shown, then you're welcome. But we did not look into this yet. The next step is indeed to work on the implications for air-sea interaction and upper air. It's clear that convection plays a relevant role. As I showed, convection is really missing in global NLUP. And of course, that has large implications for air-sea interaction, as you can imagine.
Yeah, because the results that we had looking globally at the patterns of coherent structures in the boundary layer, we see patterns that in just the distribution of what the coherent structures are globally that were very reminiscent to the patterns that you showed of error or difference between scatterometer and numerical model.
Yeah. No, so Ralph, I certainly think that it's a very good thing to check, but I did not do that yet, or we did not do that yet. So you're most welcome.
Yeah, and so maybe we take it from this week to see if we have some clever people that can figure out if SAR can help you at all with your problem. So we'll bring it back to SAR, Johnny. Don't worry.
Great. Yes.
Thank you, Ad.
Yeah.
Hello, Ad and Oris. Do you think that NSCS depends because of surface tension on temperature, and should temperature be added to the cone?
Meaning the GMF?
To the GMF.
It is for certain.
It depends on the frequency.
Yeah.
This is not the case in the C band, and I think you are now taking this into account for the KU band.
Yes, for KU band we have SST correction in the GMF. Yes.
Yeah.
And for C band, it's not. We are lucky at C band that it's not necessary. If you go to L band, you also need SST correction.
Yeah.
Yeah. And the other point on SSTs is, of course, the fact that SST gradients have a big effect on the winds itself. Yes, that is already known for a long time. And that, of course, is also visible in the plots that I showed. The fact that these biases are so constant for a long time also implies that part of it is probably associated to the ocean state, which is stable over time, rather than the atmospheric state, which is variable over time.
Any other questions or that pass time? Okay, thank you everyone. Thank you, Ed.
Yeah, thank you. Bye-bye.